kilopascal would be appropriate so that the drop does not alter the flow significantly. So the flow should not be altered so that we have to have a minimum inlet pressure of 20 kilopascal has been considered. And the S5 group, S5 T7 group alone is suitable to provide linear output from 0 to 20 kilopascal. And then you see this is for S5 T7 case with the bridge excitation of 5 volts. The change in voltage. The change in voltage is measured here for different perforation levels. S5 T7 0 to 40. We could see when the perforation increases, the output is also increasing. This is actually del V, change in voltage. But actually, our flow is nothing but the square root of differential pressure, is it not? When we are using the differential pressure flow sensing technique, we are measuring upstream and downstream pressures, and we are finding the difference of those two pressures. That is what is called as del P. That is H, head, so differential head. And the flow is directly proportional to square root of 2GH. So the flow is directly proportional to the square root of del V. Square root of del P, that is why square root of del V here. Right. This is only del V. And the another graph shows square root of del V. That's all. For all these values, I've taken square root and which is plotted here. You see, this is found to be linear to the entire operating range. Okay. So device exhibits very good linearity over the entire operating range. So this is the ultimate output of the flow sensor for the pediatric ventilator system. Similarly, for the adult, the same kind of analysis has been carried out for the design of flow resistors for the ventilator system for adults. For adults, the range is 0 to 800 milliliter per minute. Okay, so here we have found the flow resistor dimensions like L is equal to 20 millimeter, diameter 1000 micrometer, upstream pressure 20 kilopascal, flow rate 0 to 800 milliliter per minute, and the flow sensor sensitivity is found to be 0 to 2000 microvolt per volt per kilopascal of differential pressure. In all the cases, the Reynolds number is less than 2000 only. So the first graph shows the flow rate versus pressure in kilopascal. For the dimension of flow resistor is 1000 micrometer, and L is for 5 millimeter and 10 millimeter. So both are shown in the same graph. Right. And we have conducted the pressure sensor. We have obtained the pressure sensor output in millivolt like this. So the change in voltage is found to be 0.298 millivolt at 800 maximum flow rate at 800 milliliter per minute for S5 T740 case. Already we have seen that the T7 case works well for the entire operating range. So S5 T740 case, S7 T740, S9 T740. Okay, so for each and every case, the change in voltage is displayed here: 0.298 millivolt, 0.752 millivolt, 1.307 millivolt for the maximum flow rate of 800 milliliter per minute. Okay. And as we have seen already, directly I have shown the graph for the square root of del V. For the square root of del V. For S5 T7 case. For the maximum flow rate, that is 0 to 800 milliliter per minute, is shown here for the entire operating range. As the perforation increases, you can see the increase in the bridge output. when the bridge is excited with 10 volt. So this is the ultimate output of the differential pressure flow sensor, right? And these circuits has to be used externally because on the diaphragm itself we have not done. We have only the Wheatstone bridge arrangement, the wiring arrangement. Of course, I did not show the wiring arrangement. I did not show the wiring arrangement for the Wheatstone bridge. I have shown only the piezo resistors. Right. Okay. The wiring arrangements can be done on the diaphragm, but the square root extractor circuits and all not shown in the, not fabricated on the diaphragm, which are external, which are external. And for S7 T7 case, S9 T7 case. Okay. So T740 is highly sensitive in all the groups. We can see T740. So this is T740 for S5, T740 for S7, T740 for S9. T740 is highly sensitive in all the sensor groups S5, S7, S9. And the output is square root of del V is found to be 0.565 for S5 T740 case, 0.899 for S7 T740, and 1.185 for the last case, S9 T740. So now actually I have shared you the first approach, that is introduction of the perforation and the diaphragm to enhance sensitivity. That has been done, and the Tessina flow resistor was also shared. And clubbing both and clubbing them both, we have achieved the ultimate output of the differential pressure flow sensor. Right. So now approach one is over. Now we are going to look at the approach two. What is approach two? The same thing whatever we have done in approach one. The only difference is that instead of single Wheatstone bridge arrangement, we'll have dual Wheatstone bridge arrangement. Dual Wheatstone bridge arrangement. Actually, you can ask me, so why we have to go for dual Wheatstone bridge? We can have single Wheatstone bridge and we can harvest the output, which can be amplified with the help of the amplifier. That is what actually conventionally being done. But thing is that at the root level, at the basic level itself, if you can extract more output from the sensor, then the noise will not get amplified. That is the idea. But of course, somewhat difficult to fabricate. During fabrication, actually, for solid diaphragm, there is no problem. For solid diaphragm, there's no problem. We can find space to place 8 piezo resistors on the diaphragm. Already we had 4 piezo resistors. Now we have to use 8 piezo resistors on the diaphragm. And when we go for 40% perforation and all, it is somewhat difficult. Practically, so realization of those things will be somewhat a challenging job. Okay. But it can be done. So now we have technology. So we have precisely specify the coordinates for the pores, as well as we can specify the coordinates for the piezo resistor. So we can achieve that one. So in approach 2, along with the perforation introduced already on the diaphragm, dual Wheatstone bridge setup is used. That is approach 2. So already actually we could be able to achieve 93% deflection sensitivity and 83% sensor sensitivity when the perforation was introduced up to 40%. Now if you can employ dual Wheatstone bridge on the same diaphragm, then it will be doubled. The sensitivity will be doubled. Or it may be a multifold one that we are going to discuss now. The sensor which is having dual Wheatstone bridge arrangement like this is named as enhanced sensitivity external linearity pressure sensor. Here you see the same cross-sectional view of the pressure sensor with a dual Wheatstone arrangement. So additional things are shown here. And stress analysis was carried out using MEMMAC module of counterware software. Counterware software was also used only for this particular analysis. MEMMAC module was used in counter software to obtain the plane stresses in the diagram. There is the longitudinal stress and the transverse stress. Analyzed like this. Okay. And here, these four will be subjected to tensile stress. The resistors Rx1, Rx3, Ry1, Ry3 will be subjected to the tensile stress, and all other four resistors will be subjected to compressive stress. Okay. So, and this is the dual Wheatstone bridge arrangement. Actually, here we have two sets of resistors, two sets of four resistors. Normally, what we have to do? Normally, what we have to do? We have to take four resistors in the first Wheatstone bridge, like Rx4, Ry1, Rx2, Ry3. The second Wheatstone bridge, we should take Ry2, Rx3, Ry4, and Rx1. But which is not taken so due to the wiring complexity. So wiring to have a to avoid the wiring complexity, we have taken in a different way. That is, you see here, the first Wheatstone bridge, what resistors have been considered? Rx4, Rx2, Rx4, Rx2. The remaining two should be what? Ry1, Ry2. This is the conventional one. Similarly, okay, another set for the second Wheatstone bridge. But we have not taken like that. Instead of that one, so by conducting stress analysis, we have achieved this output. You see here, Rx1, Rx3 exhibit the result which is same as that of Ry1, Ry3. Rx1, Rx3 and Ry1, Ry3, the first column and the third column. So which are nothing but which are subject to tensile stress, and there is same output we have achieved. Similarly, for the compressive stress, Rx2, Rx4 and Ry2, Ry4 are same. So what I can do, I can take Ry1, Ry3 instead of Rx1 and Rx3 or vice versa. Right? Because I'm getting the same change. I'm getting the same output. So what we can do, I can take Rx1, Rx3 instead of Ry1, Ry3 or vice versa. Okay, after obtaining the results from the analysis, I have gone for different. I've gone for different way. Okay, these things are to be interchanged. Ry1, Ry3 as interchanged with Rx1, Rx3 because both sets are having same output. So I have done the wiring very easily by making this, by interchanging these values. Right. And actually here also we are placing the piezo resistors because the location of the piezo resistors is very, very important. We have placed the piezo resistors in the locations in such a way that the maximum stress which is induced on the diaphragm are harvested in the transduction process. Okay. Now let us compare the output of the single bridge and the dual bridge. And this diagram, this figure shows the output of the solid diaphragms for S5 group of sensors with single bridge, right? S5T3 deflection sensitivity is 237 nanometer per kilopascal. Operating range are different for different thicknesses. Okay. Now we are going to compare this with the dual bridge. And this, okay, that we will see now. You see here, this is a diagram which is exhibiting the sensor sensitivity in microvolt per volt per kilopascal for both single bridge and dual bridge arrangement. Okay. The green one is for dual bridge, and this one is for single bridge. You see here, actually, it is doubled. When we employ dual bridge, the sensitivity has been doubled. But in the simulation, it is exactly doubled. But in the real time, it may not be exactly double, but it will be phenomenally increased. Almost it will be doubled. Okay. In all the cases. So already we have enhanced the sensitivity by introducing the perforation of the diaphragm. Now we are further enhancing the sensitivity of the sensor by employing dual Wheatstone bridge along with the perforation. So that is the idea. Now we look at this one. I have taken 4 cases. The solid one is for single bridge arrangement, and for hollow ones are for the dual bridge arrangement, not double bridge or dual bridge arrangement for the bridge excitation of 1 volt. Okay. You see here, closely look at this, please. S5 T5 0 with single bridge. The output of the S5 T5 0 with single bridge coincides with the S5 T5 0 dual bridge. So inference from this graph is that we are able to achieve the same sensitivity, whatever we have achieved on with the help of the single bridge, has been achieved in dual bridge with higher thickness. And one more thing is that the linear range is greatly increased. The enhanced sensitivity with extended linearity. So both are enhanced here. So S5 T70, that is solid diaphragm, this one, employed with dual bridge, exhibits the same sensitivity as S5 T50 exhibits with single bridge. But the thickness T5, the operating range is only what? S5 T5. Operating range is 53.15. But for, okay, 53.15. Yes. Here you see, please mute your mic. Yeah, now it is okay. Thank you. Once again. I think it is okay now. Okay, shall I continue? You see here, same sensitivity has been achieved by employing dual bridge for the diaphragm having higher thickness. The linearity is also extended. That is the achievement by employing the dual Wheatstone bridge arrangement. Then So another case. So another set of cases have been considered. S5T3 S5T30 with single bridge whose output coincides with S5T5 with dual bridge. Okay. So these are for the solid diaphragms. So the performance was verified with ESEL pressure sensor with solid diaphragms. Now, same thing is extended to the perforated diaphragms. And here you see this is the arrangement of pores and the placement of piezo resistors for the dual Wheatstone bridge arrangement. So as the perforation level increases, this is very complex thing to choose the location for the pores as well as the location for the piezo resistors. Right. By introducing the perforation, the linear region gets reduced little bit because the rigidity of the diaphragm decreases, but which can be overcome with the help of dual bridge. Here actually 20% perforation level has been taken. Just look at the diagram. S5 T520 single bridge, S5 T720 double bridge or dual bridge. Okay. The same thing, same story here also. Whatever achieved using the diaphragm of lower thickness is achieved with diaphragm of higher thickness with extended linearity. Okay. Some other example. S5 T540 with single bridge is coinciding with S5 T740 dual bridge. That is why it is called as enhanced sensitivity external linearity pressure sensor. Okay. Almost actually we have discussed we have compared the performance of the dual Wheatstone bridge arrangement, single bridge arrangement. And the conclusion is that, so this is the important diagram. The first one, this shows the single bridge arrangement with no perforation. Here the perforation level is indicated 0% perforation, that is solid diaphragm, 10, 20, 30, 40% perforation. So this is the conventional one. So in the conventional pressure sensor, conventional piezoresistor pressure sensor, we are able to get 46.30 microvolt per volt per kilopascal. Whereas the last one, that is for the 40% perforation level with the dual bridge. Blue one indicates a dual bridge and green one indicates a single bridge for the particular case, S5T7 case. S5T740 dB with the dual bridge. We are able to get 150.36 microvolt per volt per kilopascal. That means the improvement in the sensor sensitivity is observed to be 242%. That is multifold, 3.5-fold improvement in the sensitivity has been achieved. So with perforation and dual bridge arrangement. Okay. So this is very phenomenal. So 46.30 is moved to 158.36. So this is the phenomenal increase. It's a phenomenal increase in the sensitivity. Right? That is what achieved with the help of the approach 2. And the sensor sensitivity is improved by 71%. And I hope I have shared you about my research work and hope you are able to understand my work. I'm coming to the conclusion. And this research aimed at high performance MEMS gas flow sensor using differential pressure flow sensing technique. Sensitivity of the piezoresistive MEMS pressure sensor is enhanced by employment of perforated diaphragms. That is approach one. From the analysis, it is found that the improvement in the stress level is as high as 136% with the 40% perforated diaphragm and compared to the non-perforated diaphragm. Similarly, it is found to be 93% improvement in the deflection sensitivity and 83% improvement in the sensor sensitivity from piezoresistive analysis with the 40% perforated area, irrespective of the diaphragm thickness. That was also we have seen. These findings clearly show that the sensitivity of piezoresistive pressure sensors can be considerably improved by employing perforated diaphragms. So we can say that the perforated thick diaphragms are suitable alternatives to thin non-perforated diaphragms. Is it not? And validation of the low deflection responses of perforated diaphragms obtained from intelligent stimulation are ensured with the developed to modified analytical model. And also comes from multiphysics simulation. This I did not discuss. So actually, so later on, we have gone for one more thing. The validation was also carried out with the help of COMSOL multiphysics simulation software. There also it was found to be, the deviation was found to be around plus or minus 10%. So the IntelliStute simulation results and developed modified analytical models result and COMSOL multiphysics simulation results. All are providing almost same output with a tolerance of plus or minus 10%. Then design of ESEL pressure sensors, the dual bridges excellently improve the sensitivity and linearity that we have seen. So through which we were able to achieve 3.5-fold improvement in sensor sensitivity, which was possible when combining perforated diaphragms with the dual bridges. Okay. So high resolution coupled with good linearity of the differential pressure flow sensor is ensured with high performance pressure sensors, which was carried out using IntelliStute software, and the flow resistor, which was carried out with the help of multiphysics software. Of course, actually, every system will have its own limitations. So I have discussed only, I have shared my views only from the simulation results. But if you go for the fabrication of these things, we may not get the same kind of results. Definitely some deviation will be there. Okay, so that can be only confirmed only when we realize the device. So that is why finally it is true that this research is not without limitation. The fabrication characterization of the devices designed in this research can only confirm all these claims. Okay, when we go for the fabrication or realization of the device, and when we characterize only, we can be able to confirm these claims. This is a limitation. And the future work is going to be, it is left for the future research. Hence, it is left to the future research in this laboratory, in the NPMAS Design Center at Namma University. Okay, so it has to be fabricated, it has to be realized, and then you have to check the real-time results with these things. Okay. And for more details, you can refer to the publications. So the dual Wheatstone bridge arrangement that was published in Micro Nano Letters of IET, and the perforated diaphragm implied piezoresistive MEMS pressure sensor for sensory enhancement and gas flow measurement was published in Elsevier Journal of Flow Measurement and Instrumentation. Okay, and the pediatric ventilator system and the ventilator system for adult, that work was published in Journal of IEEE. Thank you all for patient listening. Okay, hope I have not bored you. I have told you clearly. So if you have any queries, please you can ask.
Um, Thank you, sir. Thank you for your wonderful detailed lecture. We
Thank you,
hope
sir.
your lecture on diaphragm-based sensors and its practical medical applications will be very useful and
Yes, sir.
informative to the participants.
Okay,
The
thank you, sir.
analysis of the devices are very well explained. Now the participants can interact with the speaker. Participants, you can ask your queries to the speaker.
Very good morning, sir.
Good morning, sir.
Sir, I am Dr. Deepak Kumar from RKGIT Ghaziabad.
Yes,
Uh,
please.
Sir, what should be the design criteria for diaphragm structure fabrication?
Sir, I could not get you, sir. Once again, please.
Sir, what should be design criteria for diaphragm structure fabrication?
What should be the
What should be the design criteria for
design,
diaphragm structure fabrication?
design criteria?
Design criteria for diaphragm structure fabrication.
Sir, I could not get you, sir.
Sir, he is asking for fabrication, what will be the criteria of the diaphragm design? That's it.
Oh, for fabrication.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah, okay,
Uh,
sir. Okay. I know we got it. Actually, sir, to fabricate, we can seek the help of the IIC Bangalore. There is a good foundry they have, and also in IIT Pune also they have the foundry setup. Okay, we have to. There are three programs actually: the short-term, medium-term, and long-term fabrication programs they are offering. So we have to send the proposal to them, and they will ask us to present before them. And if they are satisfied with our work, if they are satisfied with our work, then they will provide us a slot, and then we can go over there and we can carry out our fabrication work, sir.
And sir, could you suggest, sir, best design parameter for good diaphragm structure as
Good
per your
diaphragm,
experience?
good diaphragm structure.
Best design parameter for good diaphragm structure.
Yeah, actually, sir, that can be fine-tuned. Actually, I have already discussed. I have done only simulations, sir, and also the analytical model results are not exactly matched with the simulation results. Some plus or minus 10% deviations are there. So what we have to do is further we can fine-tune the initial conditions. So
Okay.
we can further carry out the simulation by fine-tuning the initial conditions so that it may exactly match.
Sir, if we talking about the
Ah,
beam, then what should be the suggestible diaphragm structure?
bin. So once again, please.
In the case of the beam,
In the case of
yeah,
bin, what do you mean by bin, sir? What do you?
beam, some type of the mechanics of the beam, solid of the mechanics.
Beam, sir. Beam. He's asking for beam.
Beam. Okay, beam.
Yeah,
Cantilever type of this one.
yeah. Yes, sir.
Okay, sir. Yeah, actually, sir, you can find in literature. Already, I have also discussed. No, we can also find flow with the help of the cantilever mechanism also. So
Yes, sir.
in the flow path, we can place the cantilever, and you can choose the appropriate. You can also go for different materials. You can also go for different cantilever material, and different dimension can also be chosen and can be properly optimized. So for that one, you can better use COMSOL multiphysics software, sir.
Sir, sorry for one more question. Sir,
No. Yes.
sir, actually, sir, as per the AICT curriculum,
Okay.
the MEMS syllabus has been designed,
Okay.
and but the basic problem is there.
Uh-huh.
There is no suitable books regarding the as per AICT curriculums. So, like the mechanics of beam and diaphragm structure correlation, air damping. Sir, one more question regarding
Uh-huh.
what about the damping of perforated thick plate? Damping of perforated thick plate.
Okay. Okay. Thick. They are using thick diaphragm.
Perforated thick plate. In the case of the air damping.
Okay. Okay. Actually, are you talking about the UG curriculum, sir, or PG curriculum?
Yeah, UG curriculum.
Uh-huh. I could not get you exactly in the UG curriculum what they have.
No,
What is
sir.
the?
I am talking about, sir,
Uh-huh.
what about the damping in the case of the perforated thick plate?
Oh, okay. If you go for thick cantilever beam, if you go for thick cantilever beam, I think I'm addressing you properly. I could not exactly get you, sir. Actually, so if the thickness of the cantilever is more, then deflection is going to be less. Uh, okay, I could not understand, sir. Actually, you are telling something about which is available in the UG curriculum as per
No,
AICTE.
sir. Actually, sir, I am talking about here.
Uh huh.
Suppose I am assuming a thick plate
Okay, thick plate. Uh,
with the structure of the perforation.
okay.
Sorry, you had just telling me a lot of the innovative idea. What is the application of the perforated thick plate in the diaphragm structures?
Yes, sir. Yes,
Now,
sir.
if we apply in
Uh
the
huh.
case of the air damping,
Yes, sir. It
so
can also. Yeah. It is possible, sir. It can also be applied, sir. It can the same analogy, analogy can also be applied in the thick cantilever beam also.
no, sir. I am asking about the
Ah,
which one which one a perforation plate is the suitable in the case of the air damping, thin or thick?
thick only, sir. Thick. We have to go for thick only.
In the case of air damping also.
Yes, sir. Yes, sir. Yes, sir.
Sir, would you suggest anyone books regarding the diaphragm or air damping and structures? Anyone textbook is there? If you
Uh,
have some idea.
so, so don't worry, sir. You just get my email ID from our coordinator, and you just mail me. I will inform you, sir.
Okay, thank you, sir.
Thank you
Thank you,
very
sir.
much. Thank you very much.
Thank you, Deepak sir. The mail ID of that speaker will be shared with you. You can ask your queries through your mail. Okay.
Thank you, sir. Thank you, sir.
Now we shall conclude our session, sir.
Okay, sir.
Okay, sir. Thank you. The next session will start sharply at 11:30. The participants are requested to join the call at least by 11:25. Thank you, sir.
Thank you so much for the wonderful opportunity given to me to share my research experience with the diverse participants.
Thank you, sir. Thank you, sir.
Thank you. Thank you.
Good morning, sir. Sir, shall we start our session, sir? Raja, sir. Raja, sir, am I audible to you?
Venkatesan?
Sir, now it is audible, sir.
Okay. Thank you. Fine.
Shall we start our session, sir?
Yeah. We can start our session.
Yeah. Good morning, all. Welcome back to the second session of the day, 4. In this session, Dr. P. Shanmugaraja, sir, will deliver his lecture on biomem sensors. Dr. P. Shanmugaraja, sir, is a professor in electronics and instrumentation engineering in Annamalai University, Chidambaram. He has more than 25 years of teaching experience. He completed his BE in 1992 from Madurai Kamarajar University and obtained his ME in Medical Electronics from College of Engineering, Guindy in 1995. And he got his PhD in Nanoelectronics in the year of 2015 from Annamalai University, Chidambaram. He have published 38 research articles in international journals and more than 60 national journals. Currently, he is guiding 6 research scholars. His area of specialization is MEMS, nanoelectronics, biomedical instrumentation, embedded system, etc. This is the brief information about Dr. P. Shanmugaraja sir, the speaker of this session. Now I request you, sir, to start your lecture on biomems sensors.
Yeah, thank you, Venkatesan. Thank you. Now we can go into the session.
Sir, you can share your
Yeah.
presentation.
Yes, screen தெரியுதா Venkatesan?
இல்ல sir. So now it's opening.
Yeah, தெரியுதா போ?
Yes sir. Yes sir. You can put it in the presentation mode.
Yeah. Right.
Yes. Yeah, fine sir. Good.
Okay, thank you. Thank you.
Okay sir. Thank you.
Yeah.
Okay sir.
So I'm welcoming all the participants for the faculty development program. So today my topic is the biosensors. Okay. So my lecture is going to be some basics of sensors, and I'm going to talk about the biosensors. Then you can see the classifications of biosensors. And you can see some of the examples of the biosensor because it's a very vast area. Okay, let us see some of the basic sensors available in the market. Then finally we can see the nanosensors. Okay. So before going to the sensors, biosensors, we can see some of the basics of the sensors because that is very important. Actually, the sensors are very, very important for the complete automations. And unfortunately, even in instrumentation departments, the students are not having a complete idea about their sensors. So today in the present modern world, sensors are playing a major role because everywhere we are acquiring the data. So as per the ANSI standard, okay, a sensor is a device which provides a usable output in response to a specified measure. Okay. So normally it is a physical quantity acquired and convert into a signal suitable for processing. Okay. So why you need a sensor? So sensors are going to be pervasive. They are embedded in our bodies. We are using in automobiles. We are using in the airplanes. Okay, the best example is your cell phones. Okay, the modern cell phones, we are having a lot of MEMS sensors itself. Okay, you are having a gyroscopes inside that one. You are having a temperature sensor. Okay, even your touch screen is a sensor. Okay, so the sensors are everywhere used, and in day-to-day life, the common man is also using their sensors. Okay. And without the sensors, the industrial automation is not completely possible. Okay, you are having a countless of applications. So without sensors, there is no automations. So what are the things you can able to detect? Okay, what are the things you can able to sense? So if it is an acoustic input, okay, what are the quantity you can able to measure? Okay, you can measure the amplitude, phase, okay, the polarization, velocity. Okay. Then if it is a biological input, you can able to see the fluid concentrations. Okay, if it is electric, which is the most one, which is we are going to use in the sensor environment. Okay, the charge, we are measuring the voltage or the current. Okay, and magnetic sensors are there. Okay, we are measuring the flux, magnetic flux. Okay. And in the modern one, most of the peoples now we are using the optical sensors because it's a noise-free one. Okay. And optical fibers, okay, nowadays are commercially we are using a lot. Okay. We can measure the refractive index, reflectivity. Then thermal sensors, everybody we are using. Okay, a simple one, a temperature sensor used to measure the body temperature. Okay. And we'll have the mechanical sensors to measure the velocity, acceleration, force, and so many things. Okay. So what are the things we have to specify related to the sensors? Accuracy. This is very, very important. Okay, because the sensors are the basic building blocks of your measurements. Okay. So if your sensor is not accurate, the results are not going to be a good one. Okay, you will have an error. So this is very important in the biological environment, especially with the biosensor. Okay, there you cannot be able to tolerate the errors. Okay, so your sensors must be very accurate. Okay? And when you go for any clinical data, okay, even a small error which leads to a big problem. Okay, so accuracy is more important, and resolution. We know, everybody we know that the smallest increment of measure that a device can make. Okay. Sensitivity. This is a very important. Your sensors must be highly sensitive. Okay, it has to sense even a small changes. Okay, so it can be able to sense a temperature change of 0.01 degree. Okay, that is important. Okay, and repeatability or precision. When you are reusing or repeatedly you are using the sensors, it has to give the same input. Okay, same output for the same input. Every time when you are measuring, if it is giving a different information, different output, and it's not precise one. Okay. And other things related with the specifications of your sensor, okay, the dynamic range, okay, and linearity, that is also very important. Your sensors must be linear. And related with the transfer functions, there is the relationship between the physical input signal and the output signal. Okay. Then bandwidth. So this is important when we are working with some of the devices, especially with the biological recorders. Okay. So what sort of, when you are going for an ECG, okay, what sort of frequency you have to require? Okay, for example, it is from normally 0 to 100 hertz. Okay. Or if you are going for an audible, okay, then you can go for up to 4 kilohertz. Then noise. So your sensors must be able to withstand the noise. Okay. So again, when you are coming with the biological sensors, a lot of noises they are going to be pick up, even a man-made noise. Okay, or the electrical noises. Okay, that is very problematic when you are going to record your ECG waves. Okay. Because the ECG waves, they are going to range with the 0 to 100 hertz, and your electrical noise is a electrical frequency is 50 hertz. So normally they can easily pick up the electrical noises. So it has to be free from the noises, okay, or even man-made noise is there. So random fluctuations has to be avoided. Okay. So all your sensors must able to have a good quality on these aspects. Okay. And it has to have a various attributes, the operating principle, okay, whether it is going to be a electro-optics or whether it is going to use a active one or a passive one. Okay. What are the different sort of dimensions? Okay. Then the size. So related with the biosensors, especially with the MEMS sensors, when you are talking about MEMS, you have to talk about their size. Okay. One of the major advantage of using the MEMS sensor is the reduced size. Okay, later we can see that there is a separate slide is there. And data format, most of the MEMS sensors, they are having a digital data output, which is going to be readily accepted by all your digital devices for further processing. And intelligence. So when you are going for sensors in instrumentation side, yeah, please mute your mic. Okay, so participants, you please mute your mic. Yeah. Intelligence. So nowadays we are talking about the smart sensors in the field of instrumentation side, and that is also going to be applicable for the biosensors also. Okay. So everywhere we are talking about the intelligence smart sensors. Okay, especially in industries, we are talking about the industry 4.0. Okay, related with automations, highly smart sensor environments are going to be used in that one.
Sir?
Hello.
Sir, sorry for disturbing, sir. Kavita, sir.
சொல்லுங்க மேடம், கவிதா மேடம் சொல்லுங்க.
Sir, ஒன்றும் இல்லை சார், ஜஸ்ட் அன்மியூட் யுவர் வீடியோ சார்.
அன்மியூட் பண்ணவா?
ஆமாங்க சார், வீடியோ வீடியோ வீடியோ
வீடியோ ஆன் பண்றேன். இருங்க.
எஸ் சார். எஸ் சார்.
ஓகே,
யூ கேன் கண்டினியூ சார். எஸ்.
ஓகே, தேங்க் யூ. Then the physical contact, the way the sensors which is going to observe the data. So here also there is a classification. This is very important when you are coming to the biological environment, whether it is going to be a in vivo or in vitro. Okay, so most of the sensors, they are going to be have a physical contact. Okay, but now people are interested in the contactless sensors. Okay. Then the last one, the environmental durability. Okay, how much your sensors are going to withstand the environmental, okay, or the operating conditions. Okay. Then apart from that one, the response time. Okay, the response time should be very, very quick. Okay, that is very important related with the biological sensors also. So one of the advantages of going for the MEMS sensors is also it is having a quick response time compared with the conventional macro sensors. Okay. So when you go for any sensors, basically I'm talking about the macro sensors. We are talking about their sensitivity, selectivity, and fidelity. Okay. So the same thing is going to be applicable for the biological sensors also. So how will you choose a sensor? Okay, so what we are talking about, all these things are is related with the general sensors. It is also applicable for the biological sensor also. Okay, so what are the temperature range, the operating temperature range, the humidity effects, okay, the corrosional environmental thing, the size, okay, then power consumption. This is very, very important. Okay, the power consumption is the most important thing when you are going for a MEMS devices. Okay, because most of the MEMS devices, they are operating in the battery environment. Okay, and your sensors, when you are adapting the smart sensors, it has to consume very less power. Okay, so thanks for your the microelectronics or the nanoelectronics environment, now we are having very, very low power consumed chips are available. Okay, so nowadays the power consumption is not a problem. The battery backup can go up to a month. Okay, because this is very important when you are going for an implantable devices. Okay, an implantable pacemakers or an implantable insulin pumps. Okay, so when they are going to operate in the battery, they have to consume very less power for a longer life. Okay. And then the economic factors, the cost. Yes, the cost is going to play a major role in all sort of business. And you know that the MEMS device, okay, one of the major advantage of going for MEMS is the bulk manufacturing. Once you are going for a bulk manufacturing, the cost is also automatically is going to be reduced. Okay, so that's why nowadays we are having a cheaper devices, okay, for the healthcare environments. And lifetime achievements, how long it is going to be operated. Okay. Then related to the sensor characteristics, how sensitive, what are the range you want to measure. Okay, so if you are going for a blood pressure measurement, what is the range you want to measure. Okay, or when you are going to measure the temperature, okay, what is the range you want to measure. Okay. Then frequency response and the response time, all these things. Okay, based on these characteristics, okay, based on these factors, we can choose the sensor or you can design the sensor. Okay, so first we have to decide all these factors. Okay, then based on that we can able to design, because when you are coming to the MEMS, we are going to design the sensors now. Okay, so there is an advantage. Okay, we can design our own sensor for the given input, okay, or the given parameters. Yes, I want to measure the glucose level. Yes, I can able to design a sensor. Okay, I want to measure a pH value. Okay, or I want to measure the blood flow, okay? Or even a complicated sensors like intracranial pressure measurements. Okay, or the detection for tuberculosis or detection of cancers. Okay, so everywhere a lot of biosensors we can able to design, okay, in the MEMS environment. Okay. So that is the advantage of going for a MEMS. Some of the MEMS sensors which we had uh, shown here, the accelerometers, micro accelerometers, that is very popular in the MEMS environment, which is going to be used in a wide variety of applications, even for a structural health monitoring or for a biological environment. Okay, everywhere the accelerometers are going to be used. Okay, gyroscope, all these things are miniature one. Okay, all are MEMS based one. Okay, not a conventional macro sensors. All what we are seeing in the picture is the micro sensors. Okay, in terms of millimeters, size is in terms of millimeters, or even you can go for in micrometers. Okay, and which is going to be widely used in the commercial. Okay, the gyroscopes are widely used in the cell phones. Okay? And for pressure measurements, they are using the diaphragms. Since we are talking about the biosensors, which is going to be comes under the biomems, and we have to see the biomems also. So MEMS, everybody know that now. So biomems is a subset of MEMS, which is going to be related with the biological or the biomedical functions and applications. Okay. So the MEMS fabrication technology, which is going to be used to only for the biological applications, what we call the biomems. And any biomems device can be primarily two things. One is the sensor, the actuators, and the systems. Okay. So this is the basic architecture of a biosensors. Okay. And one of the major thing is the bio-MEMS is highly interdisciplinary. MEMS is already a interdisciplinary, okay, because you need a mechanical knowledge, you need a electrical knowledge, you need a electronics knowledge, and you need a chemical knowledge to fabricate that one, okay. And depending on the applications, you need the other civil and other knowledge also, okay. And when you come into a biomems, it will become highly an interdisciplinary area. Okay. So you need a lot of basic knowledge from the various disciplines like mechanical and material science. And nowadays the material science is a very booming area in the field of biosensors. Okay. And even in the VLSA area also, because every day new materials are going to be incorporated for the development of ICs. Because when you are using with the silicon or the carbon, is going to be available plenty in the global environment. And due to the bottleneck of the chip performance, people are using new materials, especially with the polymers also. Okay, and a lot of new materials like carbon nanotubes, nano wires, which is going to be used in the environment of biomems. And you are going to also have a things related with the physics, okay, chemistry, because a lot of polymer materials are going to be used. And when you are going for a biosensors, definitely you should have a sound knowledge in the field of chemistry, because it's highly a chemical reactive one. For an example, a simple one, a glucometer. Okay, how you can identify the glucose, okay, from the blood. So if you know the oxidation principle, then only you can able to fabricate the glucose sensors. Okay, so without having the knowledge of the chemistry, you cannot design a glucometer sensor. Okay, so what are the advantages of going for a biomems? That is introducing the biosensors in the area of biomems. So one of the major advantages, smaller volumes. This is related with the clinical side. Okay. So once again, you come to the biological, the glucometer. When you go for a conventional one, they will take a syringe and they will take normally 2 ml or 5 ml of blood to measure the glucose level. But when you are using a MEMS based glucometer, you can see that a small strip is there. You can put a single drop of blood, that is enough to detect the glucose level in the blood. Okay. So smaller volumes, this is very useful in the biological environment, especially in the medical environment. Okay. There is no wastage of the analytes. Okay. Or you can take a small samples, you can able to have lot of results. Okay. Since the volume is very less, reaction is going to be very quick. Okay, and concentrations are also going to be high. So that gives a faster result. That is an advantage. Okay, they are more sensitive. Okay, and they can use either in vitro or in vivo method. If they are very portable, and since the size is very small and you are handling very small amount of samples, okay, it is also very safe because some of the things are very hazardous. Okay, so a safer platform for handling the hazardous chemicals or radioactive materials or the hazardous biological samples having virus, even your COVID virus. Okay, so nowadays the COVID virus is also tested based on your biosensors. Okay, MEMS sensors. And lower fabrication cost. Okay, when you are going for a biosensors MEMS based one, production is going to be a mass, so that the cost is going to be very less. Okay, but again it's depending on the material we are going to use. For example, if you go for a glucose sensor, okay, the strip cost, okay, the machine is cost around 1,000 rupees and the strips are cost around some 30 to 35 rupees. Okay, because the material they are using is normally the platinum or gold in that one. That's why the strip cost is going to be very high. Okay. And some of the drawbacks of biosensors going in the biomems environment. Okay. It's a very new technology environment. Okay. And you are going to work with the human interfaces. Okay. And you need a lot of care in that one. Okay. That's why initially we had seen it has to be very accurate. Okay, and it has to have a high linearity. Okay, it has to have a quick response. All these things are we had seen. Okay, and detection principle may not scale down. Okay, and now as we are moving towards the nano level, okay, like the quantum level, okay, some of the theories, okay, like the capillary actions, all our things are going to come into the picture. Okay, you cannot able to neglect that one. Okay, when you go in the macro level, the capillary actions can be easily neglected. But when you're coming to the micro or nano level, the quantum effect will come into the picture that we have to consider for the biosensing designs. Okay. So what is a biosensor? So a biosensor is an analytical device which is going to convert a biological response into an electrical signal. Okay. It's a normal sensor which is going to convert any input into a electrical signal. Okay. So they can able to detect, quantify molecules of interest, and they are going to interact between the target molecule and a biological macromolecule. For example, a particular enzyme or a particular antibody or a particular DNAs. So DNAs are going to be detected with the help of the modern DNA arrays. The HIV virus or the the COVID-19 virus, all these things are going to be detected by means of a particular biosensors. So the current definitions: a sensor that integrates a biological element with a physiochemical transducer to produce an electronic signal to a single analyte. Let us see some of the history about the biosensors. So Professor Leland is called as the father of the biosensor. So 1916, the report on immobilization of proteins, okay, that is going to be absorbed by the charcoal. Okay. And in 22, pH electrode was developed, and 56, the Clark published his paper on the oxygen electrode. Okay. So pH electrode, PO2, PCO2, all these things you are studied in the biomedical instrumentations. Okay, these are the popular electrodes, okay, which is widely used in the clinical science. Okay. And 62, the Clark described the biosensor based on the amperometric enzyme electrodes. And 1969, a first potentiometric biosensor was developed. 1970, ISFET, okay, there is ion selective field effect transistor, which is a popular biosensors in the biomems environment. And 1975, optical sensors based on the fibers was developed to measure the CO2 or the O2 level. In 75, the first commercial biosensor was released by the company Yellow Springs for determining the glucose level. In 1975, first immunosensors was released. And 1980, fiber optic based pH sensors was developed. You can see that a lot of other sensors consequently they have developed. Then nowadays we are having the sensors based on biosensors based on different aspects. Okay. But some of the popular biosensors only that we can see only the glucose. Okay, because a lot of diabetic patients are available. That's why people are more concentrating on the sensors related with the glucose. Okay. And now in the current already we get seen the sensors are moving towards the nano level, what we call the nano sensors. We can see it later. The quantum dots, the nanoparticles, nanowires are going to be used. So in a biosensor, you are having a particular analyte, okay, the biological analyte, which is going to be sensed by the biosensor, which is going to be converted into a physical element and processed by the device. So it may be a cell, or the input may be a clinical one, the blood or urine or a saliva. So the biosensors are not only used in the clinical side, it is also used in so many other areas, okay, like food industries, okay, and in other applications are also used. So these things are going to be identified by different type of sensors. Okay, you don't have any unique biosensors. Okay, because you have to detect bacteria or you have to detect a virus. Okay, even for detecting the virus, you cannot use the same sensors. Okay, for detecting a HIV virus, you have to use one particular one, or detecting the COVID-19 virus, you have to go for some other sensors. So varieties of sensors are going to be available in the biological environment based on varieties of principles. So these are the things, the bioreceptors. It may be enzyme or it may be antibody. From the sample, you have to take, okay, you have to identify whether a nucleic acid is there, whether a particular bacteria is there, or you may identify the cells, whether RBC or WBC or platelets. Okay. And the signal transducers, it may be a optical one or it may be a MOS change, because nowadays we are using the to detect the tuberculosis or to detect the cancers. They are using the cantilever beams. Okay. When the cancer cells, they are going to be stick on the cantilever beam end, the mass is going to be changed and the frequency is going to be changed. Okay. So that is the basic principle of detecting the cancer cells by means of a MEMS cantilever beams. Okay. Only thing what you require is a particular affinity material which is going to be stick on at the end of the cantilever. Okay. And electroactive materials, which is going to be very popular in the biological environment. And we have to amplify the signals, we have to filter, okay, we have to convert into a digital one, then we have to give to the processing or for display purpose. So this is the overall view about the biological sensor, or a, we can say a smart sensor. Okay. So this is a complete data acquisition method of using a biosensors with the help of a modern display environment. Okay. So a response, a analyte, you can get a response based on the sample. It is going to be detected. Okay, the signal is going to be analyzed. So what do you want to detect? Already we have seen. Okay, whether you want to identify a protein, or whether you want to identify a particular DNA, or whether you want to identify a bacteria, or you want to identify a glucose. Based on that, you have to change your sensor. Okay, that's why I already told that there is no unique sensor. Okay, even for a single one, you can apply a different method. Okay, for identifying a glucose, you can use a amperiometric method, or you can go for a thermal method, or you can go for an electrical method. Okay, so you can apply a different principles to detect even for a single target. So how to handle the samples? Since it is a MEMS environment, okay, the fluids are mostly it is going to be in a fluid level. The input analyte is okay, and normally it is in a micro level. Okay, so you have to increase the concentration or decrease it. Okay, you have to filter, and how you are going to recognize? How do you specifically recognize the analyte? Okay. The antigen. Okay, you have to provide the antibody at the biosensors. Okay, and you have to wait for a particular antigen, whether the particular antigen is there. Okay, or you have to check whether the complementary DNA is there, or you can check the other enzymes. Okay, or the RNAs are available. Okay. So how will you specify? How will you specifically recognize the particular analyte? Okay. Based on the antibodies or based on the enzymes? Okay, or you can use the competitive binding methods by using a special polymers. So how the signals are going to be there? Okay, so when the antibodies or the complementary DNAs, they are going to touch the particular target. Okay, it is going to have a signal. Okay, so it may be an optical signal. Okay, especially with the marine materials. Okay, or some of the chemical reactions, they are going to have an optical, releasing the optical lights. Or some chemical reactions, they can go for a particular wavelength. Or you can go for an electrical method, or you can identify the MOS change. Okay, already I told that one, to identify the cancer cells. Okay, used based on the cantilever beams, the MOS directions. So only thing what you required is, based on the optical, you can change the fluorescence. Okay, it should be a high sensitive, okay, and high selectivity. And since your analyte is the sample is very small, that is at the macro level, sorry, at the micro level, we have to avoid the false signals. Okay. So only thing, when the signal or the target which is going to have a full contact with the particular material, particular enzyme, okay, then only you can able to get a proper signal. Otherwise, you will get a false signal. For example, in the first diagram, you can see that in this specific region, the particular analyte which is have a full contact, and you can see that at the last diagram, you don't have a, you have a contact, but it's not a full contact. Okay, and at the middle one, you don't have any contact. Okay, or you have to distinguish the false signal and the real one. Okay, so we have to improve the signal to avoid the noise, and to improve the selectivity. Also, we are improving the signal level. Okay, normally the signal level is very low. Okay, so you have to go for an amplifications. Okay. That's why we are placing so many materials. So how to improve that one? You can have a secondary signal amplifier. Okay, based on some additional things. Okay, for example, here they are using a magnetic bed. Okay, or a fluorescent dye. Okay, or you can use some other enzymes to amplify the signals. Okay. So already we have discussed that one of the major advantage of going for the MEMS biosensors, the size is very small, so that they can able to easily implantable in the human being. Okay. This is an accelerometer, the top one, the conventional one, and the bottom one, which is going to be a MEMS-based biosensors. Okay. So conventional transducers are very large, but they are very reliable because they are based on the older technology. And the microsensors, they are very, very small in size in terms of millimeters. They are highly sensitive, okay, but they are less robust. Okay. So why we are going for a miniaturization? So reducing the reagent volumes and associated cost is going to be very less, because some of the chemicals, they are very costly for diagnostic purpose. Okay. So we can use the less chemicals for detecting the particular targets, so that the cost is going to be reduced, and we can reduce the time. Nowadays, you can see that we are having a lot of auto analysis in the clinical labs to detect various parameters like sodium level, potassium level, and your cholesterol levels. Okay, various lipid parameters, which is going to be automatically calculated by the machines. Okay, within a less time. Okay, if you calculate it in a manual way, it will take around 24 hours. Okay, but they are giving the results within 1 hour with the less samples. So that is the advantage of going for miniaturization. That is the advantage of going for a biosensors. So the sensors can be classified, already we told that, mainly invasive and non-invasive. Okay. So invasive, you cannot able to avoid in some cases, like pacemakers, okay, or what you can say, the glucose measurements in the blood. But nowadays, people are going for alternate method. They can use the non-invasive procedure. They can able to measure the glucose level from the sweating. So everywhere we are preferring the people are wanted the non-invasive method. Okay, and that's why we are using a lot of new materials, new sensing techniques in the area of biosensor environments. This is one type of classifications of biosensors. Biosensors are widely used in both clinical and in non-clinical for both diagnostic as well as the therapeutic sites. So you need the sensors, biological sensors, for both diagnostic as well as the therapeutic. Okay, and it may be a in vivo or it may be in vitro. Okay, and it may be a long term or it may be a short term. Okay, for example, the insulin pump, which is going to be placed inside the stomach, which is going to be a long term implantable device, or a pacemaker, which is going to be assist the heart, which is also a long term implantable devices. The bedside glucose monitor, which is going to be used in the ICUs, are going to be a short term. Okay, and it may be a single shot or it may be multi analysis. Okay, your blood glucose monitor is a single shot. One time you are taking the blood and you can analyze it. Okay, and it may be in non-clinical side. You can go for other applications like environmental pollution monitoring, food monitoring. Okay, and so many other applications are going to be related with the non-clinical sites. Okay, so the biological sensors, they are not going to be only applicable for the biological environment. They are also going to be used in some other things also. For example, to identify the hazardous bacteria available in the fruits or in the vegetables. Okay, for the food safety. Okay, or the poisons or the toxic materials which is going to be available in the food, that to find out the adulterations. Okay, there's a lot of adulterations are available in the food, in the modern foods. Okay, so most of the things is some things are related with the toxics. Okay, or it may be a small amount of toxics may be available. Okay, so we have to identify that one. Okay, this is the complete picture of the classification of the biosensors. The biosensors are classified based on the receptors, that is enzyme based one, antibody one, or it may be a whole cell biosensors to identify the whole cells. Sensors based on the transducers, it may be a chemical or it may be a optical or it may be electronic one. Sensors based on the technology, nano level or surface plasma level or chip level. Okay, we are having the modern one, what we call the LOC, lab on chip. And based on the deductions, principles, electrical, electronic, or a magnetic methods. Okay. So the bottommost, the electrochemical biosensors, which are very popular in the biological environments. Okay, the amperometric, potentiometric, and the conductometric methods, different methods. These are very popular in the normal chemical analysis in the chemical lab. Okay, people are doing a lot of things in the chemistry labs. They are having all these meters. So what is an enzyme? It is a large protein molecule. Okay. So it is going to use as a tools to perform various biochemical reactions in the cells. So the enzymes, which is going to be connected with the substrates, which is going to give a complex material. Okay. Or the immunosensors, that is the antibody and antigen reactions. So these are the basic principles of biosensors. Okay, to detect the various things. Okay, the antibody, the proteins produced by the immune systems of higher animals in response to the entry of foreign materials. Okay. So this is, we can able to detect. Okay, when you are having a cold or when you are having a new virus in your body. Okay, the antibody proteins are going to be produced. They are going to bind tightly to the foreign materials. Okay, and they are going to attack to create a immune systems. So antibodies are also very specific. They have to recognize by binding to the foreign substance. So if an antigen is present, okay, it will be bounded by the antibody, and you will have an antigen antibody complex will be there. Okay. So based on these principles only, we can able to prepare the biosensors. Okay, this is an antibody structure. So you can see that one, the antigen is there. Okay, you'll have the various, this is the bottommost, you'll have the sensors. Okay. It's a particular antigen which is going to be absorbed or attached by the particular antibodies. Okay. So only thing you have to properly choose the antibodies to detect the particular antigens. Okay. Then only you can able to identify the particular antigens. So it may be the transducer may be a chemical change. So normally most of the things are going to be a chemical reactions in the body. That is going to be the key part of the biosensor. So the most common are the electrochemical, the measurements, the current is going to be generated when electrons are going to be exchanged between a biological systems. Okay, even you can have an action potential. Okay, the sodium ions are going to be transferred from the extracellular fluid to the intracellular fluids. Okay, the optical detections, refractive index are going to be changed. So optical reading, use simple pulse meters, oximeters. Nowadays, people are widely using the oximeters in the COVID time, okay, to detect the oxygen levels. Okay, so the oxygen levels are going to be measured in the fingertip by means of these optical changes. Okay, and mechanical detections, then conductometric or impediometric changes. Okay, so some of the things are related with the different transducers or the different sensing methods used in the biosensor environments. Okay. So here I had given a simple MEMS sensors for the biological environment. I already told that the cantilever arrangement. Okay, the MEMS cantilevers are going to be widely used as a detecting for various things. Okay, it can be used as a MOS one or it can be used as a laser. Okay, optical also you can be able to use. Okay. So this particular diagram which shows to identify the detect the PSA. Okay, prostate specific antigen is going to be detected. So optical sensor is going to be one of the dominant one in the environment of biosensing areas. Okay. So when light passes through that one, okay, it's going to change some of the material, or the refractive index changes is also going to be detected. Okay. So that also you can able to identify. Either you can identify the refractive change in the refractive index, or you can identify the change in the intensity. Okay. As I already told that the chemical sensors, they are the major uh, thing playing role in the clinical sites. Okay, especially with the clinical labs to detect the various things like the parameters of measuring the oxygen level or measuring the glucose level or measuring the lipid profiles. Okay. So once you are going to measure the various gases, it is going to applicable for the environmental conditions also. Okay. So related with the body, we are going to measure only the oxygen or the carbon dioxide levels. Okay, the same things, the concept is going to be same, but only thing you are changing the material. It can be applicable to measure the nitrogen or the hazardous measuring of carbon monoxides. Okay. So most of the industries now they are having a environmental measurements to detect the various hazardous gases in the environments. Okay. So the chemical sensors, which is going to be based on the different thing, the electrochemical or amperometric or the potentiometric, or it may be optical one. So various things are related to the chemical sensors. Normally there are four different type of chemical sensors are there: the chemiresistor, the chemicapacitors, and chemimechanical, and metal oxides. The metal oxide is a very popular one to detect the various gases. So the sensing materials, certain semiconductor materials, which is going to change the electrical resistance when exposed to the particular gases. So the passive chemical sensors, they are chemiresistors, chemicapacitor, and chemomechanical sensors, calorimetric sensors, metal oxide gas sensors. Okay. So just I am going to, as we are having a varieties of things, just we are seeing only the one example, chemiresistors alone. So how a chemiresistor MEMS based biosensors are going to be fabricated. Okay. So the chemiresistors are a thing which is going to be directly change the chemical interactions between the sensing material and the analyte. Okay, the resistance is going to be changed. Okay, so that we can able to measure the current level. Okay, different materials have the chemiresistor properties. Okay. The metal oxide semiconductors or some conductive polymers or the nanomaterials, the popular one graphene, carbon nanotubes. They are using as a chemiresistors to develop the electronic tank or electronic noses, what we call E-nose and E-tank. Now these two things are very popular in the biosensor environments. Okay. You cannot beat the nature because your nose can able to sense all sort of smells and your tongue can able to identify different taste. Okay. But a single sensor cannot able to identify all the different smells. Okay. To identify the rose smell, you need one sensor. To identify the H2S smell, you need one sensor. Okay. To identify a fragrance, okay, you need one sensor. So different sensors you have to incorporate as a single chip so that you can be able to prepare a E-nose. Okay. This is a very one particular emerging area in the field of biosensor. This we can skip it. Okay, the histories. Okay, this is a basic arrangement of a chemiresistor, basic chemiresistor. It's consisting of material that bridges the gap between two electrodes, which is going to be coated by a interdigital one. Okay, so what important thing is the basic concept is two electrodes, conductive electrodes are there, which is going to be connected by a sensing material. Okay, so when you are applying the analyte on that one, the resistance change is going to be detected, measured by means of the two electrodes. That's all. Okay. So only thing we have to properly choose the sensing material for a particular analyte. Okay. So this is schematic diagram to identify the oxygen sensing, O2 sensing with the help of a titanium oxides. Okay. The arrangement is an interdigited electrode. Okay. Only thing when you are going for a gas measurements, the surface area should be a very large one so that the exposure will be more, so the sensitivity will be more. Okay, that's why you are having an interdigital electrode arrangements. Okay, and the size is only in the order of microns. Okay, so the chemiresistor can be made by coating an interdigital electrode with a thin film arrangements. So you need definitely a microprocessing features to prepare this sort of resistors. Okay, so whenever you are going for a thin film arrangement, okay, without having a microelectronic processing, you cannot be able to develop it. Okay. So what are the various materials you can able to sense that one? Okay, you can use a graphene, or you can use a nanoparticles, or you can go for a CNTs. Okay, so the different metal oxides which are going to identify the different gases. For example, the chromium titanium oxide, which is going to be identify the H2S gas. For identifying the carbon monoxide and the oxygen, we are using gallium oxides. Okay, and the indium oxides, which is going to be identify the O3, okay, which is available in the ozone. And molybdenum oxide, which is going to be identify the ammonia gas. Tin oxide, okay, which is going to identify to reducing the gases. Okay, NO2 is identified by tungsten. So your material sensing is depending on the metal oxide and how pure you are applying that material. Okay, that is also very important. Okay, without any contaminations. So these oxides are already available So one of the advantage of using oxide is because when you are using a normal material, they will become oxidate. Okay, so it will become contamination. Okay. Since we are using the metal oxides, there will be no contaminations or there is no oxidation reactions in that one. And next level is converting the biosensors into biochips. Okay, artificial intelligence nowadays we are talking about. So the arrangement of combination of AI along with the biochips, definitely they will have a good role in the field of robotics. So the microelectronics, they are going to use for delivering, processing, analyzing, detecting of the various biological molecules. Okay. So you have to detect the cells, microorganisms, virus, proteins, DNAs, RNAs, okay, nucleic acids, okay. So many things we have to identify it. Okay. And we are having the modern one based on the bio sensors, what we call the LOC or what we call the lab on a chip, which is another booming area in the field of biomems. Okay, which is going to soon, it is going to replace your clinical labs. Okay, and everybody can have a small lab in their house itself. Okay, like a glucometer, the LOC can able to detect so many parameters. Okay, glucometer can able to detect only the glucose level, but the lab on a chip, which is going to be detect so many parameters. You can measure your lipid profile from your home itself. So it is a disposable one. Automation is going to be possible. Okay, integration is possible. Okay. So the future, okay, especially in the nowadays we are having threatening of viruses. Okay, the global threatening. So definitely we need the lab on a chip. Okay, to detect so many viruses. Okay. The sensors based on the materials. Okay, so far we are using the commercial devices. The conventional microelectronics are rely only on the silicon, but due to the several bottlenecks, now people move on to new materials. So many polymers already I told that one. Okay, especially the quantum wires or what we call nano wires and nanotubes. They are playing a vital role in developing so many new sort of biosensors. Okay. A lot of polymers things are going to be identified. Okay, especially the PDMS. Okay, which is going to be very much used in the biosensor. One of the uh, important thing is uh, compared to the conventional sensors, the biosensor always should have a biocompatibility. You cannot use any material in the biosensors. Okay, so you are having some restrictions. Okay, so when you are selecting the materials, you should be very careful that whether the material is a biocompatible one. That's why people are rely on the carbon nanotubes because it's highly biocompatible. Okay, it won't react with the body. Okay, you can easily place the devices based on the carbon inside the body. Okay. So when you are choosing the polymers, we should be very careful that whether the polymers is a biocompatible. Okay, there should not be any toxic. Okay. So biochip materials, you are having silicon is there, glass is there, some polymers, example PDMS and PMMA, Teflon coatings. Okay. So already I told that one, the important considerations when you are choosing the biomaterials, it should be biocompatible. And you can also consider the biodegradations, okay, transparency and rapid fabrications and chemically modified. Okay. So it should be yeah, applicable for microfabrication. It's suitable for microfabrication as well as it should be suitable as a biocompatible. So that is a restriction when you are going for a biosensor. Okay. So this is one example of colorimetric biosensor. Okay, colorimetric biosensor, they are widely used to detect the virus. If the chemical reaction is exothermic, okay, then you can go for a colorimetric principles. Okay, just we can adapt thermistors to identify the or to identify the difference between the thermal, so that you can able to identify the several uh, viruses like HIV, hepatitis B, okay, or your influenza. Okay, so many viruses, they are going to be react with some particular chemicals. So normally it is an exothermic reactions. Okay. So only thing we have to choose the particular analytes. So the top one, you can see that one, a simple colorimetric MEMS-based biosensors. And when you are talking about the biosensors at the clinical level, we have to talk about the microfluidics also. Now, nanofluidic level is also there. We are handling the fluids at the nano liter level. Okay. So the blood samples or the analytes should be flow through a microcapillary tubes. Okay, in order to have a proper mixing as well as to have a proper reactions. Okay. So this colorimetric biosensors, which is going to be have a determining of one particular virus called O157, okay, which is going to be prepared based on the gold nanoparticles. Already I told that one, nanoparticles or nanodots, which is going to have vital materials, which is going to be widely used in the fabrication of modern biosensors, modern nano biosensors especially. Okay. And potentiometric, based on the potentiometric principles, now a lot of disposable healthcare devices are coming up. Okay, in the diagram we can see that one, flexible potentiometric pH sensors, which is going to be a wearable one. So we are having a bio shirts are there, okay, which is having a incorporating so many sensors, attached sensors in that uh, bio shirts, okay, which when you are wearing that shirts, they can able to identify your body temperature, they can able to measure your ECG. Okay, also there is a wireless arrangement is there. Okay, and you are having a separate network called WSN, okay, sorry, WAP I think. Okay, for monitoring the entire body. This is widely used in the athletes, okay, to monitor their health during the training and to improve their training. Okay. So ion selective electrodes we are going to use to identify the pH. Okay. And the potentiometric biosensors, this is a wearable sensor. You can see that it's only 1 centimeter. Okay, the sensor level. Okay, and it is going to use to identify the potassium level. Okay, so it's a potassium sensitive electrode, and you can see that the sensing area is only 14.3 millimeter square. This is a piezoelectric biosensor. Normally we are using a gold, and this is an electrochemical biosensor, which is a very useful one to detect the various virus, identify the virus. Okay, like Zika or your HIV or your COVID-19. Okay, already told that one. Okay, the reason biosensors or modern biosensors are used to identify the COVID-19s. Okay, and the bioreceptors, the proper bioreceptors are going to be used, and the right hand side you can see the electrochemical signals. Okay, and optical biosensors based on the photometric principle or colorimetric principle also is there. Okay. Why we are preferring the optical sensors, biosensors? Because they are going to fabricate easily. Okay, the measurement is also very easy. Okay. As I already told that the biosensors are not only the applications are not only restricted only the biological environment, that is the human body. It is also going to be used in drug discovery, disease detection, environmental monitoring, soil quality monitoring, food quality, water quality management, okay, toxic defense. Okay. So today, a lot of military defense materials, they are going to be using the biosensors. So where you can able to place the biosensors, this is very, very important. Okay, you cannot able to place the sensors, okay, everywhere. You should have a sound knowledge about the human anatomy, okay, and where you are getting your signal properly, where your signal is going to be dominate, okay, and how to place the sensors. Okay. So it can be placed either in topical, or it is going to be placed as a internal, or it may be placed in the implanted devices. The best example is your external connected devices, your hearing aids. Okay, people are normally fix the hearing aids in the earlobe. Okay. Nowadays we are having very micro type hearing aids are there. Okay, even you can able to implantable it, okay, or you can able to implant in the cochlear level. Okay. And another example for implantable biomems is your pacemakers, and as I already told that one, the insulin pumps, okay, and defibrillators, okay, they can able to go for a implant. The biosensors normally the electrodes. Okay, when you are talking about the recorders, the electrodes are the sensors. Okay, biosensors. This is one I told that to monitor your healthcare. Okay. When you talk about the insulins, you get a micro pump. You have to measure the insulin, and you have to release the insulin level based on that. After that, you have to measure the glucose level to stop that one. Okay. So where you have to place all these things, you can see that one. You will have a different areas are there. Depending on the measurement, you have to place that one. This one I already told that, okay, biomems for monitoring purpose. Okay, wearable bio shirts. Okay, to measure the ECG, or to monitor the ECG continuously after a post-operative, that is that open heart surgeries. Okay, you cannot able to place the patient continuously in the ICC. Okay, people need the freedoms to move, walk here and there, and now wireless based wearable shirts are there. They can able to detect the ECG, and they can able to transfer the things to the doctors mobiles based on the IoT also. You see that the entire thing is going to be run on a small battery which is having 200 milliamps. Okay. This is for the biomems chip used for the drug deliveries for insulins. Okay. Not only for insulin, it can be also used for other purpose, for especially the chemotherapy treatment for cancers. Okay, or for antibiotic administratives, or for pain medications. Some people have a continuous pain in the muscles. Okay, for that also we can able to use this sort of drug delivery systems. Okay. Some popular biosensors available in the market. One popular thing is the pregnancy test. Okay, they are going to identify the particular or detecting the proteins in the urine for a pregnant woman. Okay, this comes as a strip. Okay, the urine is going to be provided in the strip, so their color is going to be changed. Okay, this is a good example for the commercial biosensors. And the glucometer is a very, very popular nowadays in the market. Okay. This the sensor is only the strip. Okay, that we have to consider. Okay, Only the strip is the sensor. Okay, the device you cannot able to consider. Okay, the biosensor is only the strip. Okay, and apart from that one, the biosensors are widely used in the uh, biopills. Okay, which is going to diagnose the uh, entire body, acting as the endoscopes. Okay, to take the images of the internal organs or to treat the internal organs. Also, you are using this. Okay, now nanoparticles are all coming the picture. To nanoreceptors are also there. For environmental applications, the biosensors are going to be used to identify the various toxins in the environment. Okay, because nowadays we are talking about the environmental pollutions. Okay, no. Because a lot of chemical industries, they are releasing toxic materials in the atmosphere. Okay. The nano biosensors, now from the micro level to nano level, people are moving with the help of the carbon nanotubes or um, the nanoparticles or quantum dots. Okay, so they are the nanotechnology opened the doors to identifying new sort of biological environments. Okay, and they are becoming the strongest tools. Okay, definitely there is no doubt in that one. It will become the future tools for all sort of diagnosing in the human body. Okay. So why we are going for nanosensors? The particles that are smaller than the characteristics. When you talk about the DNA, or when you want to detect the DNA, or when you want to treat at the DNA level, you cannot rely on your MEMS microsensors. So microsensor means you can go up to 1 micrometer level. Okay, but the DNA is around 2 to 3 nanometer level. The DNAs are at the nanometer level. So when you are going to handle or to identify the DNAs or to treat with the genetic level, okay, you have to go for the nano level one. Okay, so that's why we require a nanosensors. When the size of the structure is very less, okay, the surface to volume ratio is going to be increased considerably. Okay, so the reactions will be in a predominant way. Okay. So nanomaterials, they are going to come into the picture, and we are using the nanomaterials. People are developing new sort of nanosensors, okay, with the help of high sensitivity and less cost. Okay. Is the things giving what are the various sizes, okay, at the atom level. So when you are going to work with the DNA level, definitely you have to go for only the nanosensors. So nanosensors you can be able to use in the DNA level as well as in the uh, RNA level. The same things what we are using in the microbiosensors is also going to be used in the nano level, especially the optical, MOS, okay, and piezoelectric methods are going to be used at the nano levels. As I already told, the ENOS, okay, which is a very popular one to identify the uh, senses electronically, okay, which is going to be used widely in the defense, okay, or in the industrial environments to identify the explosives or to identify the hazardous biochemical waste. Okay, these things are going to be used. So this is a simple structure of a H2S nanosensor. Okay, you can see that the typical gap is only 40 to 60 nanometer. Okay. And nanoparticles are going to be placed randomly over the gap. You can see that, okay, the gap is very, very small to identifying the H2S gas. Okay, and By absorbing the H2S gas, okay, they are going to change their behavior. And another dominant material is your carbon nanotubes. So these things already people see or nowadays very much using in the various environment. Okay. So various carbon nanotubes, the silicon, single wall carbon nanotubes and multi-wall carbon nanotubes and your graphene sheets, they are also widely used in the biosensor environments. Not only this one, the buckyballs, what we call fluorines, okay, C60, they are also going to be used. The graphene sheets are also going to be used in the therapeutic side also. So these are the things are going to be used based on the carbon nanotubes at the nano levels. Based on the single wall nanotubes, you can identify the NO2 and NH3. Okay, you can see that they are very, very sensitive to 200 ppms. Okay, this cannot be achieved in the macro sensors. One of the major advantage of going for nano sensing is the sensitivity level. Okay, 200 ppm is not possible with your macro sensors. Okay, you can go for multi-wall carbon nanotubes, the ammonia. You can identify at 10 ppm level. Okay, that is an advantage. Okay, and you can identify the glucose. Okay, with the help of multi-wall carbon nanotubes, as well as the PVF also. Okay. And some of the carbon nanotube based sensors, different sort of sensors, electrical fit, which is going to be observe the molecules from live cells, and electrochemical methods detecting of dopamine, and fluorescence method based on the FET to investigate the exocytosis, and quenching field effect transistors based on the CNT, which is going to sense the complementary DNAs. Okay. And optical method, optical FET based on the CNTs are going to be identify the various disease in the human serums. Okay. And this one example of identifying the nano sensors. Okay, you can use the single wall nanotubes. We can say that we are saying that single wall carbon nanotube forest. That means in a platform, the carbon nanotubes are going to be placed as a pillars. Okay, in a very narrow area. Okay, in a dense way. Okay, to increase the sensitivity, we are placing the carbon nanotubes. Okay, in a denser way in a small area. Okay, so that they can able to attach the particular proteins. Okay, and they can able to identify the particular method. Okay, so earlier we had also seen that PSA, we had talked about the prostate specific antigens that can be all easily identified with the help of the carbon nanotubes. This is the nanotube strategies to identify the various PSA antigens. Okay, and you can see that the single wall nanotube forest, they can attach, they can have affinity of having the PSA antigens, so that you can easily identify the PSA. And this is a AFM image, that is atomic force microscope image. And one of the drawback when you are going for the nano sensing level is the cost is going to be very high, and to identify or to validate the devices, you need more sophisticated tools like AFM. Okay, again they are very high cost. Okay, and optical nanosensors, we are using the luminescence. The example is detecting the nitric oxide. The advantage of optical nanosensors are fast response time, and detection limit is 20 micrometer. Okay, you can see that optical sensors that contain the dyes whose fluorescence is also going to be quenched. Okay, that can also going to be sense the various ions, calcium, potassium, sodium, magnesium, zinc. Okay, this is very useful in the clinical labs as well as in the studying of the environmental also. Okay, so the contamination of water can also able to study with the help of these nano probes. Okay, and the selectivity and sensitivity of these nano sensors are very, very high compared to your macro sensors or the micro sensors. Okay. So this is the real-time detection of proteins and DNA with the help of the nanosensors, with the help of nanowires. I already told that one. The nanotubes, the nanowires, and the quantum dots, they are highly using in the modern nano biosensors. Okay. This is another nanowire sensor to detect the DNA. Okay. At the nano level also we can use the magnetic properties, okay, to detect various biological environments, to identify the various proteins or to identify the various enzymic activities. Okay. So this is a 3 to 5 nanometer monocrystalline iron oxide, a magnetic nanoparticle, okay, which is going to be you can go for a super paramagnetic principles, okay, and it can be easily detect the temperature or enzyme or the change in the pHs. Okay, so that they can be used as a biosensor for detecting various activities, enzymic activities. So this is a magnetic nanosensor for detecting the DNAs, okay, which is also widely used in the research environments. And this diagram shows the various magnetic nanosensors for measuring various enzymic activities or recognizing the various DNA. Okay. So the only thing what we require is the appropriate sensor to detect the appropriate enzymic activity or the enzyme particular proteins. And the various metal oxides are also going to be used for sensing as the biosensors. So this is a broad range of electronic and chemical physical properties are going to be sensitized. Okay. The various semiconductor metal oxides, nano belt, nano wires, and nano ribbons, they are also going to be used. Okay. So these things, okay, the nano rods, okay, and the nano dots, you can see that one. Okay, the first one is the nano wire and nano rods. Okay, and you can see that at the last end you are having the dendrites, okay, and the nano belt is there. Okay, you are having the nanospheres, nanosprings. Okay, so many things are there to act as a nano sensors. Okay, for detecting the various sort of enzymes as well as the proteins. So this is a list of, this table shows that one, the various nanosensors based on the oxides. For example, the SnO2 oxide, which is going to identify the carbon monoxide as well as the nitrous oxide. Okay, the nanowires based on the IN2 indium oxide, which is again to identify the nitrous oxides. Nanorods to identify the ethanol, and you can see that one again the SnO2, which is going to identify the dimethyl phosphonate. Okay. So all these things are, they are very highly sensitive. You can see that one, the zinc oxide, which is a very popular material used in the nanosensors to identify the ethanol. This is going to be identify the 100 ppms. Okay, so highly sensitive sensors. And this table shows the commercial accelerometers are used for the various things. Because already I told that the accelerometers are widely used in the biological sensor environments. The piezoelectric sensors are widely used to act as a hearing aids, okay, to convert your sound waves into electrical signals. The capacity accelerometers, okay, and the electromechanical sensors, okay. So various different sort of accelerometers are also used as a biosensors for as a different one. Okay, this diagram shows how the piezoelectric accelerometer is going to use in the eardrum to replace the cochlear, okay, to act as a or to help to assist the things to sense the sound waves. So the conclusion is the potential threat to bioterrorism is increasing. Okay, you can see that now the COVID-19. Okay, so there is a great need for tool that can quickly, reliably, and accurately detect the contaminating bioagents in the atmosphere. Okay, so the biosensors is not only for the biological treatment, okay, also to detect the contaminations in the atmosphere, and they are going to act as a low cost and high efficient devices, okay, in the futures. And biosensors are also going to be known as the immunosensors, okay, and the biochips and biocomputers are soon they are going to change their futures. Okay, that's all. Thank you for their patience. Okay, thank you, friends.
So, thank you, sir.
Thank you, ma'am.
Sir, thank you, sir. Thank you so much for accepting my invitation and share your knowledge at this faculty development program. I think the participants, they have gained a lot of information from your speech, especially on biosensors. So carbon nanotubes and so many things you explained. So really, it's very wonderful talk, sir. Venkatesh?
Yes, ma'am. Yes, ma'am. Sir, it was a very nice talk. Biomems and its application was being explained in various fields, especially in biomedical field. And I request our participants to interact with our chairperson, and you can raise your questions. Ms. Deepa, you can ask the questions directly to the sir. The session is open for your.
Yeah, any questions, any queries, they can.
Sir, one of the participants actually,
Ah,
her
ah.
name is Deepa. He asked the book, which book you referred. Suggest some good books for this biosensors on this topic.
Biosensor, okay. I have these things already. I have collected materials from the net only. Okay, some particular books are available. Okay, later I will give it to the madam and they will send to you. Okay, I will send a e-copy of that. Okay.
Okay, sir. Okay, sir.
Okay.
Thank you.
Thank you.
Participants, any question?
Ms. Deepa, you can ask your question directly to the sir.
What are the usage of biosensor in VLSI field, sir?
See, VLSA is going to be used in biosensor, not biosensors is going to be used in VLSA. The VLSA is going to prepare the or to construct the biosensors.
Okay, sir. Thank you.
Thank you. Thank you.
Sir, thank you very much, sir.
Thank you.
I
Thank
think
you, Anderson.
the question is over. Now we
Okay.
can conclude our second session, sir. Thank you very much for your excellent lecture, sir. Thank you, sir.
Thank you, friends. Thank you for your cooperation. Thank you.
Thank you,
Thank you.
sir. Thank you, sir.
Madam, close பண்ணிக்கலாமா session?
Yes,
Yes,
ma'am.
sir.
Yes, ma'am.
Yes,
Yes,
sir.
sir.
We
Yes,
can
sir.
end. Thank
Thank
you
you.
so much, sir.
Thank you.
Okay.
Participants, the post lunch session will commence at sharply at 2 o'clock. You can join the call by 1:55. Thank you.
Okay. Thank you, participants. Thank you.
Hello. Hello. Am I audible?
Yes, sir.
Thank you. Good
Hello,
afternoon.
yes.
Good afternoon.
Sir, good afternoon, sir. Shall we start the session?
Yes.
Yes, sir.
Please.
Okay.
Thank you.
Good afternoon, everyone. And we welcome you to the second session of the day 4, that is post lunch session of the day 4. And this session will be engaged by Dr. Sukamal Dev. He will be delivering his lecture in the title of Radio Frequency, Micro-Machined Device and Circuits for Microwave to Sub-Millimeter Wave Applications. And before that, this is a brief introduction about the speaker. Sukamal Dev earned a BTech degree in Electronics and Communication Engineering at the West Bengal University of Technology, Kolkata in 2006, and an MTech degree in Mechatronics Engineering at Indian Institute of Engineering, Science and Technology, India. Dr. Dev obtained PhD degree from the Center of Applied Research in Electronics from IIT Delhi in 2015. From August 2015 to July 2016, he was working as a project scientist in Industrial Research and Development Center, IIT Delhi. He also worked on a collaborative research project supported by Synergy Microwave Corporation USA during the same period. From August 2016 to June 2018, he was working in the Radio Frequency Microsystem Lab, Taiwan, as a postdoctoral research fellow. Since June 2018, he is working as an assistant professor in Department of Electrical Engineering, Indian Institute of Technology, Palakkad, and he is the recipient of the Postgraduate Student Award from Institute of Smart Structure and System, Bangalore, in the year 2012. Best Industry Relevant PhD Thesis Award from IIT Delhi in 2016, Postdoctoral Fellow Scholarship from the Ministry of Science and Technology, Taiwan in 2016 and 2017 respectively. Yearly Career Research Award from the Science and Engineering Research Board, Government of India in 2019, and Outstanding Reviewer Award for 2019 from the Journal of Micromechanics and Microengineering, Institute of Physics. He has authored more than 70 research papers, 1 state-of-art book, and 2 book chapters, and holds 3 patents. His research interest includes RF MEMS, microwave to sub-millimeter wave metamaterial structures, and microwave integrated circuit, including antennas, etc. Dr. Dev is a member of IEEE also. And now I request Dr. Dev to deliver his lecture. Thank you, sir. And you can start your session, sir.
Thank you very much for the introduction. And thank you so much for inviting me for this faculty development program. So could you please tell me that my slides are visible? I have already shared my screen.
Yeah, it is
Yes,
visible.
your slides are visible.
Okay. And I'm also audible too, right?
Yes, sir,
Yeah,
you are
yes.
audible.
Okay.
But
Thank you so much.
your video is not, just you mute your video, sir. Or unmute your video, sir.
Sir, you can make your camera on so that we can, the participants can view your view also.
I can understand, but I have little bandwidth issue because here it is raining
Okay.
at Palakkad.
Okay.
So,
Okay, sir, no
Okay.
problem in that. You can start your session, sir.
if you excuse me, I can turn off my video, okay, so that you can hear my voice properly.
Okay, sir. No issue.
Is that okay?
Sir, no problem, sir. You can start with your session.
Okay, thank you so much. So,
Okay, sir.
okay. Good afternoon, everyone. So, I am Sukamal De, currently as an assistant professor in Department of Electrical Engineering, IIT Palakkad. And today I will be sharing some of my works, some of the research finding on the title of Radio Frequency Micro-Machine Devices and Circuits for Microwave to Sub-Millimeter Wave Applications. So before I move into the talk directly, let me give you a very brief overview of our campus. So you can see the our campus overview. This is the IIT Palakkad current campus. And you can see the map over here where the blue color circle indicates it is a transit campus. The main campus is still under construction stage. And you know that this is one of the third generation's IIT, and this particular campus was inaugurated on 3rd of August 2015. Let me also give you brief introductions about my research group, and I mostly work on these 4 particular domains. I worked on RF MEMS, then metamaterials, microwave to terahertz imaging, and different kinds of substrate integrated waveguide structures. At present, my research team's members are, I am having 3 PhD students. Those are working on these particular topics, followed by a few BTech students. Those are also working with me. So with this, let me begin with our session. So this particular session, it is thankful to the Annamala University for inviting me for this talk. This talk, particularly the outlines, I would like to cover a wide range of RF MEMS, because whenever we are discussing about RF MEMS, and at present, especially in the era of 2021, then the RF MEMS has gone till up to a certain range that you can find applications in almost everywhere, wherever there is a radio frequency. So that's why my outline, so it is divided into primarily 6 phases or 6 parts. Part 1 will be discussing about the micro machine, different kind of switches. Then I'll be talking about phase shifters, then filters, then oscillators, followed by mixer, and then antennas. The part 7 is dedicated to current state-of-the-art RF MEMS technology that is pertaining to the sub-millimeter wave structures, followed by conclusions. So with this, let us begin with the overview of RF MEMS. So first, if you know that radio frequency, before we are moving to directly the RF MEMS, let me first concentrate on the part of RF before I move into the MEMS. So the RF stands for a radio frequency. It has a wide spectrum of frequencies that you can see. It can start from long wave radio to the visible light, and among these, it has been divided into microwave, millimeter wave, sub-millimeter wave, terahertz, all these things. In addition to that, different kinds of bands are also divided into small band, like it's starting from 1 gigahertz to 140 gigahertz. You can find a different band named as LA, CX, KUK, K, something like that. Based on their operating principle, based on the particular applications, the entire frequency spectrums has been divided into different kinds of bands. Now, if you look at the current any transceiver architecture, so I am showing you a very generic transceiver architecture where you know that these kind of architectures are available whatever be the instrument you are working on. If you are a microwave engineer, if you are using a vector network analyzer, if you are working in space industry, if you are working in the defense industry, if you are working in a mobile phone development, each and everywhere you will be finding some kind of a transceiver where transmitter and receiver both are connected with a diplexer, and this diplexer finally it is being connected with the antenna. Now, if you look at any transceiver architecture, the upper half is the receiver, lower half is the transmitter. Or in short, whenever you will find a low noise amplifier, that particular chain is the receiver. Wherever you will be finding power amplifier, that particular chain will be transmitter. Now, whenever you are looking at this, our main intention was to improve the loss. I mean, to decrease the loss so that we can improve the signal to noise ratio over a particular chain or over a particular transceiver. Now, the research was going on, started from 1998, that using this micro machining technology, to some extent, someone can achieve a very good quality factor. And if I achieve a very good quality factor, automatically I can improve the loss. That was the first intentions of development of this particular MEMS technology. Now, for any one of us, if you are working on a particular technology and if you are looking to develop a system, you have to follow some kind of a algorithm. Algorithm means, or you can say some kind of a plan. The plan is, first, once you know the technology, your next job is to go to the circuit level. Suppose I am working on radio frequency MEMS technology, RF MEMS technology. With that technology, I'll be developing my circuits. Once I have developed my circuits, I will be looking into some kind of a packaged form so that I can use it in my transceiver. So that is the device level, or you can say it's the package level. Once we have done the package level, suppose someone has done LNA in a package level, someone has done bandpass filter in a package level, connect them together to build a complete system. This is a very generic flowchart, then if that everyone follows. Followed by, let me start with the MEMS. So what is micro electromechanical system? You know that this is some kind of a system where mechanical and electrical, to some extent, the material science engineering are involved into that, and it has different kinds of subdivisions. So our mechanical engineer is working on microfluidics, pneumatics, an electronics engineer will be working on radio frequency MEMS or optical MEMS, or a biologist will be working on biomems. So now this is basically some kind of a interdisciplinary research. Okay. Nevertheless, this MEMS term, they have said in a different way in different countries. Like Europe call it microsystem technology, Japan call it micro machines. So these are the different names are available. So most likely, what is that? If you look this particular diagram where I can show you an mobile phone that was invented probably in 1985. So this is kind of a wireless, that was the wireless phone. And if you look at the chip inside, you will see different kinds of filters are there, and different kinds of capacitor resistors are also there. And also, if you are using some kind of an oscillator, that point of time, you might have used quartz crystal just to improve the quality factor so that you can improve the phase noise of an oscillator. Now, the aim was to improve all these passive circuits, the quality of the passive circuits in such a way so that you can improve the quality of the loss or the quality of the performances. How will you do that? That is the motivations. That is the motivations of today's talk. Okay. So now you can see all these red colored circle. These red colored circles are indicates that these kind of devices like filters can be easily transformed into a micro machining or MEMS technology. Followed by, the problem was that the high Q passive was a bottleneck against these kind of miniaturizations. Because initially what was happening, the mobile phone, if you look at the size of the mobile phone, it was very bulky in nature, it is very heavy, it is very difficult to carry if you compare today's current day mobile phone. Current days mobile phone are very sleek, you can always carry it in your pocket, you can go anywhere. So that is the biggest advantage, because each and every chips are being miniaturized. That miniaturized improved the technology in a wide spectrum. Okay. Now, if you look at the micro machining technology, the first thing is that what kind of process they are involved. In a very brief way, I can say that it is divided into two different kinds of processing. One is called bulk micro machining, one is called surface micro machining. The difference between these two processes are bulk micro machining, generally you are starting your process right from the substrate. You are making some kind of a deep reactive ion etching to make some kind of a cavity inside the substrate, then followed by you are making your structure on the other side. Surface micro machining, on the other hand, it is basically a layer-wise depositions, and with this help of these kind of processes, one can develop different kinds of RF MEMS devices like switches, filter, varactors, transmission lines, etc. And these are having, as I said, it is having a wide range of applications, because radio frequency is almost applicable almost everywhere. And in the bottom, you can see different kinds of bandpass filter, MEMS phase shifters, all these kind of things. Now, we will begin with first thing is the switch. So now switch is something like that is very important, whatever be the applications we are working on. If you even don't consider the word micro machine, if you consider a simple switch, that if we consider a simple switch, then first thing that come to our mind, that is some kind of a PIN diode switch. Exactly the switch, what it does, whenever you are turning it on, signal is going. Whenever you are turning it off, you are basically stopping the signal to flow. The same principle is being used, but in a different way to develop this kind of micro machine switches. Okay, so let us go discuss on that. What is all about micro machine switches? Whenever you are talking about a switch, irrespective of any complex, anything, the first two categories of the switches are shunt switch and series switch. What shunt switch does? You can see that the shunt switch basically, like whenever you are sending a signal, basically if you are not giving any actuation voltage, the signal is passing from input to output. Whenever you are pressing the switch, signal will be grounded. What happens to the series switch? Exactly opposite to the shunt switch. Now, if I develop this kind of switch using a micro machining process, the first what I will do, the first thing that is important, the substrate. Once you know your substrate, next thing is this substrate can be a silicon substrate, can be aluminum substrate, can be a glass substrate. On top of that, what you need some kind of a transmission line to flow your signal. You need to have some path on which your electromagnetic signal will be propagating. So the most of the cases in terms of a micro machining process, the transmission line that we have chosen, it is called coplanar waveguide. The coplanar waveguide is something like that. At the center line, it is a signal line. Either side of the signal line, you can have the ground. That you can always see it in this diagram. The middle line is the same signal line. Either side of the middle line, you can find the ground, and that is actually going with your circuit. Now, what are you doing it over here? You are depositing some kind of a dielectric layer. You can see it from the blue color. The blue color is the dielectric layer. Then you are depositing some kind of a sacrificial layer. The name itself is very interesting. The sacrificial layer, once you have deposited some kind of a sacrificial layer, say for an example, 2 to 3 micron of sacrificial layer, after that you are making 2 windows, then you are basically depositing these kind of beam that is called bridge. Okay. At the end of the process, you are basically removing all these layer that you named as sacrificial layer. So as the name suggests, this particular layer has to be sacrificed at the end of the process. Once you have sacrificed this layer, you can find some kind of a air gap between these two. After that, what will you do? You will basically apply a potential between this ground with respect to the signal line. What will happen then? It will create some kind of a potential difference between this bottom to top conductor. Once you create this potential difference, then it will find some kind of a force, electrostatic force, and beam is also having some kind of a force that is called restoring force or mechanical force. Up to a certain point, bridge mechanical force will be fighting with your electrostatic force. But electrostatic force is always in your hand. You can always control it. So now, once your electrostatic force will be more than the beam restoring force, then entire bridge will snaps down on the dielectric. So now, if you look at it in this way, so once you are not applying any voltage, your signal is passing from input to output through the center line. Once you are giving a particular voltage, then the entire beam is snapping down, touching with your signal line, then the entire signal will be grounded. You can always represent it with a very simplest equivalent circuit model that is showing over here. Now, what happens to the series switch? Similarly, this is your signal. In this case, you are basically keeping the series switch or keeping this kind of a cantilever type switch beam on the top of the signal line. Now, when you are also keeping a dedicated bias pad, you have to understand the difference between these two. Here, you may not need a dedicated bias pad. Your signal line, center line can act as a bias pad. But here you need a dedicated bias pad to actuate the beam. Now, what is happening? When you are not applying any voltage, you will be getting, all signal will be grounded. Signal cannot pass from input to output. You can see there is a gap. When you are applying some kind of a voltage, the entire bridge will snaps down, and there is a, you can get a connections from bridge to the signal line, and the signal will be passed from input to output. That is the simplest way one you can differentiate between the working principle of the shunt and series switch. Now, let me show you a nice animation so that your concept will be much more clear. This animation shows it is some kind of a switch. You can see that there is a it is a beam which is perforated with some holes. You can see it over here. And what is happening over here? This is the signal line. These two are ground plane, either side of the center line, and you can see this beam is actually you can relate with this particular structure with the help of this schematic. This schematic is showing you that there is a two dedicated bias pad on the either side of the center line. You can see it. These bias pads are sitting over here at these two locations. Now, what is happening when you are not giving? First of all, this is what kind of switch it is. It is a shunt switch. So now, what I will be doing it over here, I will be applying some kind of a actuation voltage. Okay, once I apply, initially I don't need to apply any actuation voltage. When I will not be applying any actuation voltage, signal can pass very nicely from input to output. You can see it from this white color arrow is moving. That is means your signal is passing. Now you are applying an actuation voltage. You can see you are applying these two bias pads, the blue color bias pads. Those are internally connected with each other, and you are applying bias with respect to this beam, with respect to this particular ground. So now, when you are creating a potential difference over this area, then what is happening? The beam is snapping down. And when the beam is snapping down, the entire signal is grounded. Okay, so this is the very basic way to tell you how a switch is actually working, a shunt type switch in a practical environment. Now, if you look at the comparison between a pin diode switch or any solid state devices with respect to the RF MEMS switch, you can see this particular table is a very informative table where you can see that actuation voltage of this kind of MEMS based switches are very high as compared to the pin diode or FET switches. But one should not be worried about this particular thing, because the advantage is the current. The current is very, very less. It is in microampere range, which is very, very negligible. Followed by the pin diodes are also having similar, also having some kind of a current that is 3 to 20 milliamps, and FET is also having a very less current. So now the MEMS is giving you an advantage in terms of power consumptions, that is VI product. If you multiply this VI product, this particular term in terms of milliwatt will be very less. Now, one of the other advantages of MEMS technology is the loss. You can substantially improve the loss of these switches. If you look about the isolation, which it is greater than 40 dB as compared to the pin diode and FETs. If you look at the insertion loss, it is very, very lesser than pin and FET. So this is the thing. Okay. Now, when you are, so first, now you know the difference between these kind of switches with respect to the other solid state counterparts. Now, if you are planning to develop or planning to work on the RF MEMS switches, you have to follow a systematic, you have to make a systematic work plan. What do I mean by that? A systematic work plan means this kind of research involves different kinds of measurements. Because here, whenever you are buying a switch from the market, a pin diode, say for an example, or if you are making a filter, you need to make a reconfigurable filter, or if you are making an antenna. So for for this purpose, you are buying a pin diode switch from the market. Whenever you are buying a pin diode switch from the market, you will be getting some kind of a data sheet where everything will be mentioned, like what is the actuation voltage, what is the loss, what is the isolations, everything will be mentioned. But here, when you are proposing your own switch, you have to make your own data sheet. That is very important. your first job is to make your own data sheet, and to make your data sheet, you need to do a couple of measurements to qualify your switch for certain applications. The first thing is that if you look at this flowchart, the first thing is the design. Once you have the design, you have to fabricate your device. Once you have fabricated, if you have this structure with you, do the profile measurement. It means what? It means you have to see that because of some stress involved in the beam, sometimes beam can curls up. If it curls up, then maybe your actuation voltage will be more. Then again, you have to take that data, put it in your simulator. Again, you have to simulate it in terms of actuation voltage. Then you have to measure the mechanical resonance frequency. Once you have made the mechanical resonance frequency, then you have to measure what is the pull-in voltage and release voltage. What is that? Pull-in voltage is the simplest way I can say it is an actuation voltage, and release voltage is some voltage where the beam is coming up, okay, or it is moving up to its initial positions. Then you have to measure the switching time and release time. What is the time it is taking? This particular thing is very important if you are planning to apply or planning to make your switch for defense and space applications. Then temperature stability. How much temperature it can sustain, and it is also a function of power handling. If your switch can sustain high temperature, automatically it can sustain high power. After that, you have to see what is your intermodulation distortions, I mean non-linearity measurement, or third order intersect point, in short IIP3. So once you have done all these things, then your last stage is very important, because whenever you are making a switch, your aim is not to actuate it only one time. You want your switch to be actuated nearly billion cycles. So now, for that reason, the reliability measurement is very important. If you are happy with your reliability performance, then you go to the packaging stage. If you are not happy, again, you change your design to some extent so that you can reach to your desired level. So here you can see a few diagrams. That is the top diagram, it's called laser Doppler vibrometer. This is basically to measure the mechanical resonance frequency. Then this particular thing you can see, it is something like a actuation and release voltage measurement. This is a loss measurement. You can see a VNA, a circuits, everything over here just to measure the loss. Now, here I would like to give you, just take one example. Here I am showing you one example of the switch, where a switch, you can see now, you know, this switch is being placed on a center line. You can see this is the ground line. These two are ground line, middle line in the center line, where input and outputs are written. On the middle line, these cantilever type switch are being present over here, you can see. And in the bottom, you can see some kind of a black rectangular patch. What is that? This is nothing but an actuation pad. And you can see there is a connections over here. This is some kind of a high inductance. It is basically an RF choke. So followed by a bias pad. Now, what are you doing it over here? If you recall the working principle of the series switch, when you are not applying any voltage, your signal will be isolated. When you are applying a voltage, you are applying potential here with respect to this pad, this cantilever beam will touch to the output line, and you can get a nice flow of the RF signal. Now, with this, the first measurement that you have to do, if I follow my previous flow chart, first thing is to measurement of the mechanical resonance frequency. Then you can see this is the measurement of a transit and release time. This is the measurement of the actuation and release voltage. You can see actuation and release voltage measurement is nothing but the capacitance versus voltage. You can see this is the graph where it is following some kind of a hysteresis. At a certain voltage of 39 volt close to, the beam is snapping down. Again, there is a decrease in the capacitance. Again, it is moving up to its initial positions at the values of close to 25 volt or 23 volt. So the 40 volt, close to 40 volt is the actuation voltage, and the release voltage, it is close to 23 volt. So this is the actuation voltage. Then the loss, you can see this is the leftmost one. It is showing you return loss, that is matching, then the isolation, and the right one is the insertion loss, that is giving you the switch. So this particular switch is giving you close to 0.4 dB of insertion loss, up to 20 gigahertz, which is quite a good number. And if you look at the isolations, the blue color graph, the isolation, it is showing you something like close to 15 dB. So rest of the things are also a very good number. Then you have to measure the non-linearity performances, like a third order intercept point, then followed by the power handling. This particular switch can handle 1.5 watt of power. You can see it over here. After that, there is a sudden decrease in the level of the voltage. So this is the way you can measure the power handling. Now, once we have the single switch, if you look at the isolation, let me show it to you in a much more detailed way over here. So once you have these isolations, if you look at this particular graph, these isolations, these insertion loss, or this matching performance, you can always validate with a given formulas. These formulas are already available. From the measured data, do some back calculations, find out what is your capacitance, what is your resistance, what is your inductance. Once we have these RL and C values, make a simplest circuit model in any circuit simulator like ADS and see your performances are matching or not. Okay. Then followed by, you can always measure the non-linearity performances, like you need to have two signals, give to nearby frequency, give it to a power combiner. This is your device under test, and you see it in the spectrum analyzer to find out the non-linearity. Now, if you look at this particular thing, the next, if you look at the isolation, as I said, it is close to 17 dB. You can see the blue line. Then we are thinking that how to improve the isolations. The easiest thing that we thought about, if you look at this particular structure, in this structure, before I explain you the structure, let me explain to you the basic schematic. Here, what we have done it over here, you can see this is the input line. In the either side of the input line, we have connected two switches, and these two switches are ground. And in the line itself, I am having one switch. Now, what is happening over here? If you apply a signal, now if you can correlate with this schematic with this particular image, it is a fabricated image where these two switches are the shunt switches, and if there is a series switch. What is happening here? When you are not applying any actuation voltage, then your signal is going through this path and signal will be grounded. Okay. So now when at one time you are basically actuating this and this switch, I mean the switches, those are connected to ground. Now when you are applying this kind of bias, the signal will be grounded, and if by any chance there is a leakage in the signal, it cannot even pass to the output because this particular switch is non-actuated mode. So entire signal will be grounded. If by any chance there is a leakage, that signal cannot pass from input to output. So you should get a great improvement in the isolation. And that is quite observed from here. If you look at the measured data, you can see the isolation is showing is S21, and the isolation, it is achieved 48.23. The isolation is better than 48 dB. Initially, we are having the same switch, single switch was giving us close to 17 dB, but it has improved to 48 dB using this particular technique. Now, the similar kind of technique can be used to develop different kinds of switching network. Switching network means it is some kind of a single pole double through switch or single pole multi-through switch. It means one input, multiple output. Now, if you look at this particular switch, here you can see this is a single switch. And before I explain it to you, I just forget to mention, all details of these particular switches are available in this paper. Each and every slide, I have given you the source of this paper. If you can always look at these papers for the more information. Now, for this particular switch, what is happening over here? You can see the input is over here. You can see the output. These are two output lines that is referred by P1 and P2. Input is going here. The signal is, so you are actually doing the same principle. You are applying one series shunt switch. This particular topology is called series shunt configurations, one series, two shunt switches. So in short, you can call it series shunt configurations. So these series shunt configurations are used in either side of the signal line. When you are activating this particular P2 arm, then your signal is grounded. Your signal is passing from input to P2, and at one time signal can pass from input to P1. And at the simultaneously, the top graph is showing you the signal which is passing from input to P1, and in this case it is input to P2. So, and it is the overall performance. You can see it is a return loss of better than 20 dB and other thing. And the other losses are also in acceptable range. But look at the isolations, it's a close to 40 dB isolations that is achieved from DC to 20 gigahertz frequency, which is quite a good number. Now, the similar concept, similar way, one can also develop different kinds of other things, like if you look at a conventional type single pole 4-through switch. I mean, if you are having a single input line, you can see there are 4 arms. On top of the 4 arms, you can see there is simplest shiny things. These are the switches. These are made by gold. And these switches are basically like 4 switches. You can clearly see it from here. 4 switches are sitting on the 4 arms. And based on the actuations, each and every arms are activated, and you are getting the signal in the other 4 ports. So this is the input port, other 4 are output ports, and this is the way you can see the performance. This performance is showing you this switch is operating from 13 to 18 gigahertz. It was designed for some specific applications, for a defense applications that is working at Ku band of frequency. Now at the same time, one can improve the performance by using the same series shunt configurations. You can see this is a series switch, these 2 are shunt switch. You can see a close zoom diagram of this fabricated image. So this is the way you can improve the isolation to some extent. If you look at the isolations profile, it's quite good. 28 dB isolations you are getting it better than, and the other and the return loss and everything, it is at bit higher stage because number of switches are more. See, there are basically 2 things over here. First thing is that either you can improve the isolations. While improving the isolations, you have to use more control elements. Now, once you have used more control elements, like then automatically each and every control element will contribute to some loss, right? Insertion loss, because you are inserting some extra component into your device. So this addition will give you some kind of an increment of your insertion loss. That you can see it over here. Previously, this is but if you look at it, is up to you. If you design your structure in such a way, you can always mitigate some kind of a loss, or you can always improve the loss performance. If you look at this particular profile measurement data, you can see this particular switch is giving you close to -2 dB loss, but till up to 60 gigahertz, which is quite a good number. From DC to 60 gigahertz, this switch is operating. Okay, so with that, let me start with a second phase of my talk. Now, up till now, you know that what is the control element that is being used. So switch is very important. Once you have the switch, then come to the current scenario. And now I am taking you back to the current era of the communications, where everyone is looking for 5G, or the 6G is also knocking the door. So whenever we are talking about this kind of communications, the main important thing in any communication channel is the RF front end. In short, RF-FE. Now, whenever you are looking at the RF front end, then you have an antenna. With the antenna, there are different kind of switching network. You can see this is the one question that may come to your mind before that. We are happy with one switch, single pole, single through switch. Then why we should make single pole multi-through switches? That's SP40, SPDT, or maybe higher than that. So the need is the current scenario. If you look at the first diagram, this diagram is showing you a direct conversions architecture. In the direct conversions architecture, you can see there is a switching network followed by different filters. Those are connected at each and every point. If you consider with these 3 lines, if you consider that this particular switching network you are using, that is SP3T, single pole 3 output, 1 input 3 output switch. Then in every arm you are connecting one band pass filter. So this is the way. So at this, maybe this band pass filter is working at 1 gigahertz. This band pass filter is working at 2 gigahertz. This one is working at 3 gigahertz. And your switching network is working from DC to 20 gigahertz. So now, so you are basically making some kind of a channel select filter, so that at each and every time, whenever these particular things are required, you can see current mobile phone can, if you can have the Wi-Fi data, can take the Wi-Fi data. That time it is working at 2.4 gigahertz. Current mobile phone, it is, if it is 5G, it is operating at 3.5 gigahertz. So in the mobile phone, you are basically at one point of time it is working at 2.4. At one point of time it is working at 3.5. So now you need to have some kind of a channel selections automatically when you are turning on or whenever you are pressing a button in your mobile. So this process has to be very fast. So now this is the current architecture. This is the diagram of a the direct conversions architecture. This is the diagram which is very, very well known to you. That is the super heterodyne receiver. This is the architecture that is called low noise amplifier multiplex module, in short LMM. And this is the architecture where you can see that it is an integrated radio front end with an antenna array. So the main target is what? Main target is written in blue colors. So now all these blue colors, see, antenna, switching network, band pass filter. For time being, forget about LNA. Then mixer, voltage control oscillators. So all these things are basically creating a giving you a very important information that you have to have a good quality devices, followed by it has to be miniaturized to meet with the current architecture, to meet with the current requirement. So if we follow these things, then I have already started discussing on the switch, also give you a glimpse of SP single pole multi-through switch on SP40. Then probably I have to have more number of switches, like I have to improve the quality of the switching network so that we can connect multiple filters simultaneously. So this ignites us to go into the details of making of different kinds of switches. Like you can see here, SP60 switch where single input 6 output, SP70 switch single input 7 output. You can see P1 to P7. This is SP10T single input. When this is the, you can see this is the circular line where all these switches are connected, and every switches are connected with some arms. This is SP11T, SP12T, then followed by SP14T. I repeat, SP14T. It means in one input line, and all these images I am showing it to you, these are fabricated image. These are fabricated image where you can see this is the input line. This is P1, P2, P3 till up to P14. So all switches are connected over here. Signal is going here based on where it is getting a shorted path. Signal is following. Shorted path means the respective switches are connected and signal can easily travel to that particular path. Now, all these switching networks were designed up to X band. You can see this is the 12 gigahertz. So where we had a comparison, so you can see these switches are giving greater than 14 dB of matching, followed by insertion loss of 1.76 dB, whereas the isolation is 14.5 dB up to 12 gigahertz. Nowhere you can get this performance if you are using a CMOS switch, if you are using a pin diode switch, if you are using any other solid state counterparts. So only the micro machining technology can give you this kind of performance if you design it thoroughly, if you fabricate it, if you measure it nicely. Then not only SP6, SP14T switch, I will show you some even a higher order switch also. Now let's come to the phase shifter. Again, go back to this particular module where you can see whenever you are working on this highly integrated two-dimensional radio frequency front end, one of the important device that is available is phase shifter. Phase shifter is a very, very important device, and let us talk about the phase shifter for a while. This phase shifter is what? The phase shifter is basically giving you some kind of a phase shift with respect to the frequency. Okay. So now, when nowadays the phase shifters are coming up with some kind of a, they call true time delay phase shifters. Okay. And the utilizing the MEMS technology, the phase shifter, the loss of any phase shifter plays a very important role. I mean, you can improve the loss up to a certain extent. And these phase shifters is always gives you a guarantee to a linear variations of the phase shift with the frequency. Now, if you remember the different kinds of phase shifters, that is the reflect line phase shifters, that is called switch line phase shifters, that is the called loaded line phase shifters, low pass, high pass phase shifters. All these are basically giving you the different phase shift, different kinds of phase shift as per your need. Let me tell you a very basic, let me give you some kind of an explanation on a very basic topology of phase shifter, that is switch line phase shifter. What it does, it is, you can see there is a reference arm that is blue color, and you are connecting a delay arm that is in the red color. These reference arm or delay arms are connected with the SPDT switches. You can see there's a single pole double through. What are you doing over here? You are passing a signal from input. You can see the arrow of the switch. You are passing the signal through the reference arm, getting the signal stored. Now you are change the locations of the switch, activate the second arm, and take the signal through this delay arm. What will happen? Because of the line length difference between the blue arm and red arm, you will be getting, if you compare the phase between the reference arm and delay arm, you will be getting some kind of an additional or differential phase shift. This is the way we generate different kinds of phase shifts. So if you now, this is one of the other example. If you see low pass, high pass section is very simple. Again, you are connecting two SPDT switches. In between two SPDT switches, you can see this is one arm is the low pass arm, one arm is the high pass arm. Low pass will give you some kind of a phase delay. High pass will give you some kind of a phase advance. Between the delay and advance, it will give you some kind of a differential phase shift. So the micro machining technology have been used extensively to develop. Now what we did basically, here I will be presenting most of the things what we have developed. So now we have chosen the two basic topology, that one topology that I have already explained, switch line phase shifter, and the next topology is called DMTL phase shifter. So DMTL stands for distributed MEMS transmission line. Now what we are doing it here, you can see the gray color line is the coplanar waveguide, where center line is the signal line, either side of the center line is the ground line. All these, then this kind of a CPW line is loaded with these blue colored beams. These blue colored beams are nothing but a MEMS bridges. Now, what are you doing it basically over here? Let us take an example of initially whenever I was not putting this bridge. When I am not putting these bridges, I am taking the impedance of the line is 75 ohm. Now, when I am adding the bridges, I am increasing the capacitance that is loaded in the line. Now, when I am increasing the capacitance means automatically impedance is reducing. So the 75 ohm is reduced to 60 ohm. Now, your next job is just to actuate the bridges to get it, just to actuate whenever you are making actuations. Again, you're increasing the capacitance. I mean, the capacitance which is occurring between the center line with respect to the bridge over this overlap area. You are basically, what are you doing it? You are basically increasing the capacitance, reducing the impedance a lot to get it close to 50 ohm. So basically, you are basically moving from 60 ohm to 50 ohm. So while you are moving from 60 ohm to 50 ohm, when you are getting the 60 ohm, when you are not actuating the bridge. When you are actuating the bridge at some voltage of V1, then you are getting a 50 ohm. So during the 0 volt to V1 volt of actuations, you are basically getting two phases, and you are comparing these two phases to get your desired phase shift. So this is the way this phase shifter works. Now let me show you the one example of the phase shifter. So here you can see this is you can see the top diagram over here where it is showing 11.25, 22.5, 45, 90 degree, 180 degree. So these are the different unit cell of the phase shifters. So say for an example, if you are developing a 5-bit phase shifter, 5-bit means 360 divided by 2 to the power 5, your lowest significant bit is 11.25. That is the way I started it with 11.25. Next higher digit is 22.5, 45, 90, so on. So now you can see the topology is the switch line topology. You can clearly see that two SPDT switches are connected over here. And when you are activating these two switches, getting the signal in the reference arm. So basically, what are you doing it over here? You are basically getting 32 states from a single device. 32 states of phase from a single device based on the actuations of these switches, based on the different combinations, based on the 32 combinations. Now, if you look at this particular phase shifter was developed with for the applications of defense, for applications of the DRDO. In this case, they were looking for some reliability. Now come to the factor of, say for an example, you have made a nice phase shifters. Those are giving you a very good loss. But at the end of the day, you need a very good quality reliability cycle. The reliability cycle means what? You need to operate these switches billions of times. Now, there is a problem. The problem indicates whenever you are making this switch line topology, what is happening over here? If you connect the number of switches for a 5-bit phase shifter, there are 20 switches. So the number of control elements plays a very important role in micromachining technology. You have to make a topology in such a way so that you can drastically reduce the number of control elements. So if you look at it, this particular structure, it didn't work well in terms of reliability. It works up to 200 cycles. But having said that, let me remind you one more thing. Whenever we have to understand the difference between a reliability of a switch and reliability of a device like phase shifter. What is happening if you are working on a switch? Whenever you are actuating a switch for a single time, you can call it 1 cycle of reliability. If you actuate 10 times, you will call it as 10 times of reliability. So you can say my switch worked 10 times during the operations. But you cannot claim the same thing whenever you are making a phase shifter, whenever you are testing a phase shifter where 20 switches are connected. Nevertheless, it is a device. So that device should give you 32 phase states. For that, you have to measure 32 times. You have to measure the devices 32 times to say when you are getting all 32 phase states, then only you can consider it 1 cycle of reliability. So is 1 cycle for a single switch is equivalent to 32 states of 1 cycle of a phase shifter. That is the challenge. Now the next challenge is to how to reduce the control element. So that the topology that we proposed over here, this topology is telling you is that here we are using SP40 switches followed by 2 SPDT switch. What is happening over here? We have made the phase data in such a way so that you can see in this particular case, if you compare this case, to activate one state, I said I have to actuate 10 switches. But here to activate, say for an example, to get the reference state, say for an example, 0 degree state, how many switches I have to activate? Only 6 switches. 1, 2, 3, 4, 5, 6. Only 6 switches needs to be activated on a single arm. Initially, I was having 10 switches. Now I am having 14. So only 6 switches. So there is a drastic improvement. But if you look at the return loss and matching, it is also quite good. this particular phase shifter, once it is developed, then it is diased, and then it is make it in a kind of a low cost package form. You can see different kinds of lines. These are basically the bias lines. Finally, you can see these particular switches are basically activated with some kind of a driver circuit over here. Through the driver circuit, this particular phase shifter worked up to 10 million cycles. Okay, so this is the way this phase shifter works. Now, the time has come probably. I told you that I'll show you one higher versions of the single pole multi-through switch. Before I move into that, let me tell you one thing. Now from here, I got an idea that yes, if I reduce the number of switches are placed per arm, as I said, there are per arm, there is 6 switches. Now, if I reduce the number of switches per arm to some extent, then probably I can improve the reliability. That is the one thing. Second thing is that now once I have developed a switch, once I tested a switch for one time, and when I'm telling it it's a one cycle of reliability, at the same time, can I say the same thing when I'm making the device? What do I mean by that? While in the entire operation, one switch actuates only one time. Because if you look at this particular topology, multiple switches are operating over the one cycle time. Okay, here also the same thing. But say for an example, I would like to make a device, a phase shifter, where one switch will work only one time. So throughout the operations of the 32 states, the switches one switch operates only one time. So if I developed a good quality switch, then if I place the same switch on a phase shifter, then probably my job will be done. Exactly on the line of the same thought, we developed a phase shifter like using a single pole 16 through switch. You can see there is one input line. On the input line, you can see there are 16 switches. You can see P1 to P16. You can find 16 switches, all these arms, and these are rounded CPW line. You can see this is the CPW line, those are passing by. Okay, and all these switches are connected over here. Now, based on the actuations, based on your requirement, whenever you are giving a shorted path, the signal will go. And then what we did, once we have the SP16T switch, then we connected the SP16T switches back to back. When you connected SP16T switches back to back using the same switch line topology, what will you get? You will get, there are how many lines are there? 16 lines. 16 lines will give us what kind of phase shifter? 4-bit phase shifter, right? 2 to the power 4, that is 16. So the 16, it is basically giving you a 4-bit operations. Now, in this case, what is happening? Over the arm, only one switches are activated only one time. Okay, so now in this case, you can see this particular phase shifter was operating at 20 gigahertz. You can see it's a narrowband phase shifter, and this also operated at something like a 1 billion cycles. Here I'll show you the reliability data, not going into the details of it. If you have any questions, feel free to ask me later. Now, if you look at the return loss performance, it is greater than 14 dB. Insertion loss is 1.9 dB, quite a good performance. So this particular is a 4-bit phase shifter. Now, one can again give some counter argument that, okay, you are saying that you are using 2 SP16T phase shift switches and connecting them together, and you are claiming that at one time one switches are operating. But if I look at holistically, I can see 32 control elements. SP16T1, SP16T2, there are 32 switches. So the 32 switches are quite a huge number in terms of fabrication also, or in terms of operations also. So although you are reducing the loss, but at the same time, or although you are improving the reliability, but it is a very risky process. And exactly we have seen the same thing while making it. We have developed almost 10 phase shifters like this, but out of 10, 2 phase shifters work perfectly fine and nicely. Most of the phase shifters was failing after a few cycles of operations. So the problem is the figure of merit. The problem is the aspect ratio. Okay, just to improve that, then I proposed one topology, that is a novel topology, where I connected SP6 switch line phase shifter for and DMTL phase shifters. What we did over here, we took two SPNT switches. Exactly, if you look at this particular diagram, here this is a switch line phase shifter. Now, if I load the bridge, if I load the lines with some MEMS bridges, then automatically I can add these two topology. Okay. Once I added these two topologies, switch line and DMTL phase shifters, you can see the nice schematic over here, where these are the delay lines and the gray color lines are the bridges that is making the DMTL. So by doing that, I achieved something. What is that? This is a nice idea. So after that, what we did, if you look at it, here, if you look at the first diagram, that's just next to the schematic, here you can see it is a SP40 switch. You can see closely, you can see SP40 switch, 1, 2, 3, 4, 4 lines are connected. SP40 switch and back-to-back one SP40 switch, and all these lines are connected. Now, each and every lines, you can see some kind of a bridges. You can see close, the zoom view it over here. So these bridges are connected on the line. Here also, if you look at it, this is the first one, it is a 3-bit phase shifter. This particular one, it is a 4-bit phase shifter. Now, if we look at the 4-bit phase shifter, there is a SP80 switches. You can see 1, 2, 3, 4, 5, 6, 7, 8. 8 arms are there, SP80 switch. Now, here, what is happening? Here, you can see there are two bridges are connected, and these bridges of different bridges are connected over here. Now, what is happening? Now, here I am saying that I have used two SP80 switches. But when I was explaining the last slide, I said that I developed SP 4-bit phase shifter with SP16T switch. SP16T switch. But here I only used SP80 switch. So I already get rid of 16 switches. Only 2 SP80 switches and then the varactors. Now you can say again that you might have used a varactor over here. But the varactor, the beauty of varactor is that it never snaps down. If it snaps down, because the varactors, if you look at this diagram over here, the zoom view, these varactors are connected with two ground lines. Now the varactors will only actuate it up to a certain limit. It never touch to the center line. It will give some capacitance variations. Okay. So while doing that, so basically, like if you look at this, one line is giving you two phase data. You can see every line, it's red color, it is marked over here, 0 degree, 22.5 degree, 90 degree, 112.5 degree. So every single lines are giving you two phase states. So initially one single line was giving you one phase state. Now here we are working on a single line that is giving you a two phase data. Okay, so with that we have drastically somehow experienced a good results. If this particular phase shifters tested up to 1 billion, then the test was stopped, and it is giving us some kind of a 1 billion cycle of operations. But on the drawback of these things, you can say the actuation voltage, because the actuation voltage is 110 volt. But the point to be noted here is that if you have to make the actuation voltage very high to some extent, because in a current day architecture, always you'll be having some kind of a charge pump that can boost up 3.3 volt to 110 volt. But high actuation voltage will ensure that yes, your switch is basically mechanically stable. So when the switch is very mechanically stable, then automatically you can improve the reliability up to a certain extent. That is the overall idea. Now the losses, if you look at the losses of the phase shifters, it is quite a good number, but insertion loss was bit higher side. It is close to 5.4 dB at 35 gigahertz. But I can always say 5.4 dB at 35 gigahertz is not that much of high if you compare it with the CMOS switches or any pin diode-based switches, diode-based phase shifters. So now, I'll give you some kind of a glimpse of other different types. Up till now, I discussed in details about switches and phase shifters. Now I'll give you some kind of a glimpse of current day filters and other devices. Now MEMS filter, the filter, you know that whenever we are making the filter, I'll just give you one example of that. So the image that you are showing it over here, this particular filter was developed for a 5G applications. And this is a band pass filter using the micromachining technology. Now, the band pass filter, whenever I am making a band pass filter for a particular applications like a 5G, so the 5G basically it is operating at a different frequency. It works at 3.5 gigahertz, it works at 28 gigahertz, 39 gigahertz, 60 gigahertz, different kinds of small bands are located. There is no point, if you are using a micromachining technology, there is no point of making some device at a lower frequency, because you can always make it with some pin diodes, get a nice loss. But MEMS you should use it when you are targeting at a higher frequency. Here we have targeted at 28 gigahertz frequency. So now you can see this is the table which is given over here, 28 gigahertz, where you can see these particular filters, it is a band pass filters, and this band pass filter, how it is designed, I am not going into the details of it. Entire details will be available to you, I will tell you. So now here we have done it, you can see this is the simplest block diagram or the circuit schematic, where there is a switch, you can see there is a series switch, followed by you have series capacitor, shunt capacitor, then series inductor, then the shunt inductor. You are basically repeating, you can see the center line of symmetry, the either sides are similar. So you're basically, what are you making it? You are basically making some kind of a band pass filter with some tunable components like varactors, like switches. Now you can see the array of switches. The array of switches is basically giving you some kind of a capacitor bank. So you can see there is a capacitor banks you are forming. Then this is, it is also some kind of a capacitor. It's a variable capacitor. It is made by two bridges. There are no switching actions happening over here. I mean, the switching action may happen over here whenever there is a cantilever switches are connected. Now what is happening over here? You can see there is a 28, you can see the band pass filter response. The band pass filter response is showing this particular response. I'll show you in a detailed manner. So this particular response, with the help of this variable capacitance tuning, you can see this over here, you can tune the frequency from 27 to 29 gigahertz. You can tune it from 27 to 29, and you can track the individual center frequency like 27, 28, 29, like that. Nevertheless, with the help of the tuning, you can also increase the bandwidth. You can see the bandwidth tuning at 28 gigahertz. Obviously, I'm showing you the simulated data over here. I'll show you the measurement data also. So now this, you can see by changing the capacitance, you can tune the frequency. Now that the bandwidth tuning is responsible by the series arms, like the series switch array, like the block 1 I mentioned over here. The block 1 is responsible for bandwidth tuning. The block 2, that is this shunt capacitance, the block 2 is basically responsible for the center frequency tuning. So now this particular filter can tune the bandwidth and the center frequency both simultaneously. Now I'll show you the measured performance of this. Once at one time of tuning, you can see this FC is at 27.4 gigahertz. A fine tuning will help you to reach it at close to 28 gigahertz. Then again, if you tune it, it can go to the 29 gigahertz. And all these responses, you can see it over here, all these responses are compared between measured and simulated. Okay. So now, if you look at the magenta color things, it is also showing you the bandwidth improvement. So the magenta, I have only used the highest bandwidth improvement as compared to the initial stage. So you can see if you compare the blue line, that is the measured line, the blue line with respect to the magenta line, you can clearly see the difference between the bandwidth improvement. Okay, similar thing is applicable here also. So this is the way this filter, the entire details are available in this particular paper. It is available in the recent Jan 2021. It's in IEEE transactions on microwave theory and techniques. So all entire details are given in this paper. I request you to go through this paper if you have more, if you want to know more about this particular topology. Now moving forward, the filter, not only that, the switches are also only responsible to develop the filter. If you currently one term that everyone is saying almost, that is the software defined radio. The software defined radio, cognitive radios, in those kind of things, the RF channel selections is very important. So the RF channel selection is so important, like that I have already told you that one switches are connected with one filter. This is, and then entire thing is connected to an antenna. Finally, it is becoming like an antenna terminated spectrum analyzer. So now, whenever you are making such kind of a cognitive radio, the important thing, the bottleneck of this thing is the kind of power. I mean, the power consumptions. So the MEMS will give you a very good power consumptions. Now, in addition to that, only not the switch by which you can make the filter. There is also one more versions of the RF MEMS along with the switch, that is the resonator. So the resonators are also used extensively to make different kinds of filter. I'll show you some of the glimpse. Leftmost side, you can see the piezoelectric based resonator. In the rightmost side, you can see a capacitive resonators. Piezoelectric and capacitive resonators are basically used. There are three different transactions mechanism. First is called capacitive based transactions, then piezoelectric based transactions, then piezoresistive based transactions. These kind of different ways you can make the resonators. After making the resonators, you can make a different filters. But most likely resonators are being used at a lower frequency, but you can use it in RF MEMS. So where you can see this particular filter is working at 15 megahertz. Okay, so if you are working at a very low frequency in megahertz range or to 1 or 2 gigahertz range, use this resonator to make the filter. If you would like to work at 28 gigahertz or 10 gigahertz, use switches to make the filter. That is the way you differentiate. Okay, so I am not going into the details of it, but again, my source is written over here. Always you can take a look on this and get more information. I'll just show you the applications of where these MEMS, this RF MEMS is in the current practical scenario. Okay. So now, even though just one information I would like to give you, in 2019, one paper was published in Journal of Microelectromechanical System. So where you can find a filter which is based on a resonator that is even working at 4.5 gigahertz. So they are basically coming to that higher range. Okay, even you can find a filter which is operating at 10 gigahertz also. So the resonator-based filters are also competing with the switch-based filter over the MEMS platform. Now, give you a quick glimpse of the oscillators, MEMS-based oscillators. So what is that? Again, the MEMS-based oscillator, if you look at any oscillator circuits, you can see, if you know, there is a sustaining amplifier, followed by in the feedback, you have to have a resonators. If you recall oscillator, only one thing that everyone knows, that is the Barkhausen criteria. Criteria says that loop gain has to be greater than unity, loop phase has to be equal to 360 degree or 0 degree. This is the Barkhausen criteria that has to be fulfilled. Now, for that, once you have the sustaining amplifier, once you have made the sustaining amplifier, then in a CMOS technology, then you can make the resonator using the MEMS technology. Now, the advantage of the MEMS technology, I have been keep on telling that the quality factor. You can get a very good quality factor using the MEMS resonator. Now, quality factor plays a very important role when you are making a filter. Simultaneously, quality factor plays a very important role when you are making an oscillator, because oscillator phase noise, if you look at this formula, the oscillator phase noise is inversely proportional to the square of the quality factor. So now if you improve the quality factor drastically, you can automatically reduce the phase noise. Now, if you look at the quality factor, so which component will improve the quality factor? Needless to say, the resonator. The resonator will give you the high quality factor. And if you make the resonator using MEMS, you can drastically improve the quality factor. So now in the oscillator, you can see, so the whatever things I'm showing it to you, now let me show you a practical example or the practical applications, how it is being made. Now, in this diagram, you can see exactly the top one. It is the sustaining amplifier. It is being made with TSMC 0.35 micron process or 350 nanometer process. After that, this is the circuit diagram of the simple MEMS resonator. Now you can see in the yellow color, it is showing you the CMOS chip. This is the MEMS chip where you can see the resonator. Now this transimpedance amplifier and resonator, you connect them together with some additional bond wire and you check the performance, look at the power, measure the phase noise and other thing. And this is the way, see, if you look at the phase noise, it is giving you some kind of a 100 or 110 dBc. Okay, so this is the way you can always make this kind of oscillator using a MEMS. Now, MEMS-based mixer. Mixer, you know, it is basically mixing two components. When if your F1 giving F1, giving F2, how will you make it in a mixer? So MEMS is also being used to develop a mixer. How do you do that? I'll show you a nice example of it. So this particular thing, what is happening over here, you can see this is some kind of a resonator. You can see big rectangular box. It is a resonator, but this resonator is being designed in such a way that you can get RF, you can get 3 arms. So see, in mixer, you need to have 3 arms, right? One is RF, one is LO. LO means the signal that is coming from the local oscillator. So signal which is coming from the local oscillator, RF signal is passing on, then there is some kind of a mixing is happening, and then you can get the RF and LO can be mixed up and they can generate the IF. It is basically happening the down conversion. So RF and LO are multiplying them together to get the IF stage. That is basically it is being made using this topology. Now this topology, whenever you are making a mixer, one of the very important point is that whenever you are giving RF signal and the signal which is coming from the local oscillators, these two signals should not be matched, should not be mixed. So you have to decouple this signal. For that, you have to also measure each and every stage isolations. It means how RF and LO are decoupled from each other, how IF and LO are decoupled from each other, how these RF and IF are decoupled from each other. 3 stages you need to measure. So now you can see this is the measurement data of RF and IF, RF and LO and IF. So here you can see that this isolation is better than 40 dB. It's quite a good number. Now one more thing is the conversion loss. That is one of the important category of the mixer. So I'm not going into the details of it, but one of the advantage of this particular topology is that this kind of mixer, it is basically operating as mixer and filter both. Okay. So now, so these mixing and filtering stage are happening simultaneously. And as I said, entire details, if you are interested on to know on this, details are given, sources, informations are given. You can check my paper and get the information. Okay. So I'm not going to the details of it. Now let me come to the last phase, that is the antenna. Antenna, I think everyone knows how it operates. It is basically playing an impedance matching device between your guided structure to the space. So the MEMS-based antennas are widely available. So I'll show you the two antennas. That these particular antennas, if it is being made with a SPDT switch, you can see this is something like a switch, an antenna which is operating at 60 gigahertz. Okay, so the point here is that exactly I was telling you, whenever you are using the MEMS technology, preferably you take it to the high frequency. There is no point of, if you are using a switch, there is no point of working at a low frequency. Okay, that is one. Second point is that if you are making it at a low frequency antenna, what will happen? Your patch size will be too much big, right? So if you are having a high patch size, because whenever you are measuring it, the chip area is also very important. If you are making it from any CMOS process or something like that, 1 centimeter by 1 centimeter tiles will be given to you. Okay, so preferably you make your antenna at a high frequency for a better performance. Now you can see the SPDT switches are connected between two antennas. These two antennas are nicely radiated. One is horizontally polarized, one is vertically polarized. You can see the positions, the way they are placed. This one is vertically polarized antenna. This one is horizontally polarized. So based on the actuation between arms, you can either get a horizontal polarized signal or you can get vertically polarized signal. So this particular thing, you can see the measured data. It is working at 60 gigahertz frequency very nicely. We have also measured the antennas. This particular antennas is, we have also measured the switch. This switch is also operating quite nicely between 2 to 4 dB scale. And also this is the radiation pattern. You can see there is not much of cross to back radiations. There is not much to have the back radiations. Now, one of the other examples I'll show you is it is something like this particular antenna is operating at 77 gigahertz, and these antennas, advantage is that this is basically antenna that is polarization reconfigurable. You can reconfigure the polarizations based. It is basically a circularly polarized antenna. Either you can get left-handed circularly polarized or right-handed circularly polarized based on the certain actuation scheme. So I am not going into the details of the scheme, what kind of actuation scheme, what kind of topologies are being discussed over here. I would like to just wanted to show you that yes, MEMS is being used drastically, not only the switch just to make a switch, but also make a different kinds of antennas, filters, and other thing. And the details of these design, details of the performance are again, it is available in this paper. Interested readers or the interested audience can go through the paper for more information. With this, I'll conclude it with a note that current days, if you are using the MEMS, I have been keep on telling RF MEMS has now reached to a certain level where it is being used at terahertz also. Okay, so the terahertz, it means that highest, it is the frequency mostly after 140 gigahertz, you can use it at 220 gigahertz, different kinds of, but you need to have an idea to use it. That is very important. That's why I have shown the yellow color bulb. You need to have that idea to show it, to operate it at a terahertz, even at a high frequency. How will you do that? So now you will see that if you are working in the MEMS at a sub-millimeter wave region, then that point of time, there is something like some techniques, some topologies are working on the frequency selective surface. So you can see the MEMS are being used to develop different kinds of frequency selective surfaces. And this is the simulated data I am showing it to you, which is this. At present, we are working on it at a terahertz level MEMS. So this particular design is being made. You can see there's a band pass filter. Now, if you look at this diagram, this is a transmission. This band pass filter is operating from 0.6 to 0.95 gigahertz. You can see it over here. So this band pass filter 0.52, or you can say if you take the 3 dB loss, you can see it from 0.5, 0.6, 0.5 to close to 0.9 or 1 terahertz. So this is a wide range of band pass filter, and it is working at the terahertz region. Now, when you are making this filter at a terahertz region, you are basically like, you are not doing any on-wafer measurement. You are basically like, you are sending us RF signals, high frequency signal to this particular surface, the yellow color surface, and then you are basically doing some kind of a spatial filtering. For that, your TE and TM mode of propagation is also important. I'm not going into the details of it. This particular work is ongoing. And And then similarly, you can use, that metamaterials is also is one of the very many researchers are working on the metamaterials. Using metamaterials with the help of MEMS, you can make a very beautiful structures. I'm showing you some kind of a diagrams over here. These kind of metamaterial based surface are giving you also some kind of a filtering actions. You can see this is the filter which is operating at 0.36 terahertz. Okay, that is 360 gigahertz. Okay, so and in addition, so all these responses, whatever I am showing it to you, it is only up till now it is simulated versions. So we have not yet fabricated it, but we are planning to fabricate it soon. So this is the way you can think about the MEMS now. Now, this is also one of the structures where you can see there are different kinds of cantilevers are being placed, and this particular work was reported in one of the conference where their researchers are making using MEMS technology to get a terahertz, to get a filter at terahertz domain. Okay, and this domain you see, it is basically from close to 1.1 to 1. Somewhere at close to 1.2. So this is a very narrow tuning range. It's very nicely it gets tuned. Okay, so now they are taking the RF MEMS technology till up to the sub-millimeter level to the terahertz range to get the performances. Now with this, I would like to acknowledge my PhD supervisor. I did PhD from IIT Delhi, my Professor Shivan Kaul. I also worked in Synergy Microwave for 1 year. I thank my collaborators, Dr. Ajay Poddar, my postdoc supervisor from whom I learned many things on this particular MEMS technology. I worked with him for 2 years. I also acknowledge my collaborator, my funding agency, that is SARB, for funding me so that I established a nice anechoic chamber, and MMIC, that is Microwave Monolithic Integrated Circuit Laboratory at IIT Palakkad. And with this, I would like to thank the Department of Electronics and Instrumentation Engineering, Annamala University, and also very special thanks to Dr. Kavita, who keep on contacting me, updating me about this FDP program, and for inviting me to this program, for sharing my thoughts and deeds with you. Thank you so much, Dr. Kavita, for inviting, and thank you all for giving me this opportunity to present my works to you. Thank you so much.
Thank you so much, sir. Thank you so much for accepting my invitation, and you shared your vast knowledge with us, sir. It's more informative, and we have gained a lot of information from your speech on this particular topic, sir. Thank you so much, sir.
Thank you so much. If you have any questions, feel free to answer me, or if you do not have any questions right now, feel free to send me emails. My email IDs are given over here. You can always write to me if you want to know anything on my talk.
Yeah, participants, if you have any queries, you can ask the speaker now.
Dear participants, you can ask your question. You can raise your question with us, sir.
Okay, then the speaker's mail ID has been given to everybody. Yes, Deepak sir, you can ask the question.
Sir, good afternoon, sir.
Good afternoon.
Sir, I am Deepak Kumar from RKGIT Ghaziabad.
Yes.
Sir, could you suggest anyone book application of MEMS in RF area?
You want to know the book?
Yeah, in RF area regarding the MEMS resonator design consideration, 1-port micro mechanical, 2-port micro resonator modeling, like that.
Okay, sure. I can ask you. I can tell you is that there are 2 books are available. Very good books. Okay. The first book is written by Professor GM Rebiz. GM Rebiz.
GM Reddy.
Rebiz, Rebeiz.
Okay, sir.
GM Rebiz, RF MEMS Theory and Technology, something like that. Okay.
Yes, sir.
The PDF of this book is available in online. You can check it. Okay.
Okay, sir.
One more book that is also I can tell you, I can suggest you, that is also, that one more book is there that is very much focused to switches and phase shifters of RF MEMS. That is actually written by me. You can also, I can share, I can give you the link to that. It is published in CRC Press in 2019. Okay. So this book is basically whatever the things I forgot to mention it in my slide. That book is also giving you entire information of this talk. You can get an overall idea about how to design a switch, or how to design a switching networks or phase shifters. Okay, so this you can see it in my IIT Palakkad website. The link is given. Okay.
Okay, sir.
In my profile you can find the link, and you can also get that book. It is not that much that much costly. You can get it, and you can keep one copy in the library. That is a very good book. In that book, if you have any doubts, you can always ask me. Okay.
Yes, sir.
Yes, these are the two books where you can get it. Okay.
Okay,
So the first one where you can get wide varieties of RF MEMS devices, but the one what I published, there you will get a very focused applications only on the switches and different varieties of phase shifters and switching networks.
Okay, sir. Thank you, sir.
Thank you very much, sir. Is
Thank
anybody else? If not so, sir, today we can conclude our session today, sir. So thank you very much for your excellent talk, sir. Thank you, sir.
Thank you so much. Did I take more time, or I finished it within the
No,
No,
it's
sir, you are on time, sir. No
actually
problem with that.
one thing I learned from you learned from IIT, sir, because you have that management, time management and all. We have learned from you all people, sir.
So nice of
Because,
you. So nice of you. Thank you so much.
thank you so much, sir. Thank you so much. Okay, sir.
Thank you so much.
We can wind up this session, sir. Thank you, sir.
Okay.
Okay.
Thank you. Sorry, I was unable to share my videos.
It's okay, sir. No issues, sir.
My apology.
Okay, so
Yeah.
that's one small request. Actually, all
Yes.
the participants, they are asking the materials, sir. The PPT, PowerPoint, what you make. So just you mail me, sir. I forward to the participants. Okay,
Absolutely, I will do it. I will
Yeah.
do it just after this. Means shall I send it to you to your email ID? Is
Yes,
that okay?
yes, sir. Yes, sir. My mail ID you send it to me, then I forward to all the participants.
Sure,
No
sure.
issue.
Absolutely.
Thank you,
Absolutely.
sir.
I'll do it. I'll do it.
Okay, sir.
Thank you.
Thank you so much.
Thank you for inviting me once again.
Thank you, sir. Thank you, sir.
With this, we are concluding our today's session. The participants, the attendance link and feedback link will be sent to your registered mail ID. Please fill it up and send it as soon as possible. Tomorrow's session will start at 9:30 a.m. sharply. Thank you, everyone. Thank you all.
Tomorrow, and one more thing, Venkatesh, in the afternoon you should write the test actually. So tomorrow
Yeah,
morning
that
you
will be. Yes, ma'am.
So tomorrow, tomorrow is the last date, no? So when the test will be, what is the time for test? So that and all we will inform tomorrow. Okay.
Yes, ma'am.
Okay. Okay. We'll wind up.
Okay, thank you all. See you tomorrow. Bye.
Okay. Thank you.
Thank you.